Good morning, everyone. We are waiting for 5 minutes for the whole students. So, in 5 minutes, we are going to start. Thank you.
Hello, good morning.
Good morning, Google. We are waiting for a few minutes more, 2 or 3 minutes more to wait for the students. Number is growing, so we will start very soon.
Okay, okay.
Okay, good morning, everybody. I think that we have enough students to start with our last day of Perovskite PV Summer School of the Apolo project. So today we're going to be a different day compared with the previous one, since during the morning we're going to have a session dedicated to flexible perovskites and also applications that can show you a more real world of the technology. During the afternoon, we are going to have a special session dedicated to the project, where the idea is to see how Apollo project is taking in account all the facts explained in the talks that we had in the previous days, and to give you a general overview of what we are achieving now, what is going to be next, and what is the application that we are going to deal with in this project. So I'm glad to present you the first speaker. We have the Dr. Francesca De Rossi from the University of Tor Vergata in Italy. She has a PhD degree in telecommunications and microelectronics engineering on flexible bisolar cells by the University of Rome in Tor Vergata. And she worked 4 years in a technology transfer fellow at a specific innovation and knowledge center, Samesa in UK. She was part of the PV team focusing the scaling of printable perovskite solar cells, and she led on the stability activities of the group during this period. She's currently a fixed team researcher in the University of Rome, Tor Vergata, funded by the European project Apollo, that it's the project that it's organizing this event. So the Francesca talks will focus on the advances on new generation flexible printed PV, mainly perovskite solar cells, of course, and flexible substrate and printing techniques will be reviewed, reporting the latest results about layered edge flexible printed modules. So thank you very much, Francesca, for coming and present your work here in the summer, and all the floor is yours, please.
Thank you, Anna. Good morning, everyone. I'm going to share my screen. I hope you can hear me well, and hopefully I can put my presentation in the presentation mode. I'll ask Anna or Joan to confirm that they can see my screen, okay?
I think it's okay, Francesca, we can see it.
Very well, so I'll start. Okay, so as Anna was anticipating, we are going to talk this morning about printing techniques for mainly perovskite solar cells on flexible substrates. Just a quick introduction of our group. So we are at the University of Tor Vergata in Rome. Here is where the Colosseum is. We are a little far away from it, but we have very nice views from the university. And this is the building where our labs are hosted. We are also known as the Center for Hybrid and Organic Solar Energy. And we are a quite big group working on several different European and Italian projects. So we have gave, let's say, birth to also some spin-off companies, and we run an international school on hybrid and organic photovoltaics, if any of you is interested, called the ISOFOS. Not sure it's going to happen this year, but I mean, it's a quite valuable one. So our main research focuses on printed electronics and photovoltaics via the device design and fabrication. And we try to bridge the gap between the academic research and industry. These are the PV technologies we research on. So organic photovoltaics, disolar cells, and perovskite solar cells. Since this is a school on perovskite solar cells, obviously I'm going to focus on this latter technology. So we all seen this graph several times, this chart. My only intent is to bring your attention on two characteristics of both OPV and perovskite solar cells, and before them disolar cells, which is the let's say unique feature of solution processability of such technologies, which implies that potentially they can be fabricated by a low-cost manufacturer. Okay, so if we think about moving from small to large area, as you can see from this graph here, obviously we are losing some efficiency going from from rigid to flexible. So the red one is the current record on a small area on rigid glass substrate, 25.5%, while the orange one is the current record on flexible substrate. Then again, when we move from this small area to larger areas, we lose something else. But still, you can see that the gap is not so large. So when we talk about moving from small to large area, the first consideration that we can make is that we need proper printing and coating techniques. In this review, which is cited here, you can find detailed description of all these techniques that I'm going to talk about, giving a brief overview. We can divide them in two main classes, which are, the proper printing techniques and the coating techniques. So is coating, as you can see, like spray coating, the spin coating, which is the most widespread technique that we all use in our labs, dip coating, and the doctor blade. Is proper printing, like screen printing and inkjet printing, and when these some of these techniques are applied and are used in a roll-to-roll configuration, we have like these more complicated setups. So another classification that we have to have clear in mind is the difference between a sheet-to-sheet production and a roll-to-roll production. So the main differences are related to the throughput, so the speed we can, so the speed we obtain the coated layers, and also the let's say that the investment that we need to set up these systems. So while the sheet-to-sheet production is characterized by low throughput, but potentially lower capital expenses, so the money that we need to set it up, roll-to-roll methods are characterized by high throughput and high capex as well. So we need like a larger budget to set up a roll-to-roll line. Just to go back, to our main subject, which is the technology, the perovskite technology developed on flexible substrates. I just want to give you an overview of the possible flexible substrates and their main features. So all of them are characterized by high power to weight ratio. This is why potentially they are preferred in space application compared to rigid and high weight glass. they can be conform on any surface, so they could apply for both building integrated photovoltaics and for building applied photovoltaics, which is a kind of retrofitting on existing buildings. They are for sure compatible to roll-to-roll fabrication. And usually they are low cost. So the most common one I would say are polymers, mainly PT and PEN. So like recently, some groups have been working on ultra thin flexible glass, included us, which has the same flexibility as polymers, but it can withstand high temperatures. Same for the metal foils, which have the drawback, which is their opacity. So they are not transparent. So if you build a solar cell on them, you have to shine the light on them from the back, let's say. And there are some less common substrates, still quite interesting, which are paper, just cellulose paper, you know, the one that you use for, I don't know, your notebook or whatever. And the ceramic material called muscovite, sorry, I don't know how to pronounce it, mica. So they've been reported like very recently, some perovskite solar cells on such substrates. So if we look at the features of these different materials, we can see that some of them can withstand high temperatures if you look at the thermal properties. Some others, like the PET, will require low temperature processing because over 150 degrees, they will deform and even just melt. So paper at some point will burn. So yeah, we prepare like this table with the smiley faces just to summarize which substrates have good properties and which have not. And this is for a chapter that we are currently writing with my supervisor, Professor Brunetti. So just a quick highlight on these peculiar flexible substrates, which are the paper and the mica. So paper obviously is very interesting because it would be a super cheap substrate, widely spread and available, and also easily recyclable because you could just burn it and you would have the recycling issue kind of solved. About the mica, this is quite interesting because it can be transparent, so like the polymer, but it can withstand high temperature, and it looks like it gives like more stability to the devices. If you look here in the left bottom, you will see perovskite layer grown on mica, and they remain black, so they don't degrade at this quite stressful condition of high temperature and high humidity. Right, so let's go back to the coating technique. So the spin coating is a technique that I guess all of you have experienced at least once. So we have here a cheeky video to show how it works. So we just dispense some solution on top of a substrate, and when we activated the equipment after a ramp acceleration, the substrate will just spin, and this constant rotation would thin the film, and we will obtain the desired thickness. So usually quite thin films can be obtained in this way. The let's say, the speed that we apply, the angular velocity, will determine the thickness. So higher the velocity, thinner the film, and also the concentration of the solution will affect the final thickness. So if we want a thinner layer, we would use a less concentrated solution. Okay, so about the formation of the film, we have to keep in mind this like mechanism. So at the beginning, the thickness is reduced while the substrate is spinning to less than 2 microns by just the radial displacement of the material over the substrate. Then at some point, the thinning is just dominated by solvent evaporation, like in this area. And this helps an in situ crystallization. So this is quite an interesting features of the spin coating, and is possibly the thing that we are going to miss when we use other techniques for the deposition of thin film. Now, on the other hand, we have to have clear in mind that the spin coating is a quite wasteful technique. So I just made some calculation, and I mean, from our experience in the lab, and you will need for a square meter like 160 milliliter of solution, while if we just use the blade coating for obtaining the same extension of the film, so 1 square meter, we would need just 5 milliliters. So we are talking about 2 orders of magnitude less than what needed for the spin coating. The other problem with spin coating and moving from small cells to larger substrates is kind of the limit that the spin coating offers, which is related to the batch processing. So it's a quite low process if you want to produce a high number of devices. And the other thing is that we are kind of constrained on the size of the substrate that we can use. So in our lab, we've been able to spin coat perovskite solution on substrate as big as like 5 by 5 centimeters square, or even a little more. But obviously you cannot do like an A4 size substrate in a spin coater. So which coating and or printing techniques can we adopt to replace the spin coating for large area substrates? Well, the decision is not easy because there are several techniques, and each of them is characterized by different features. So some of them waste more ink, some of them allows the creation of a pattern, some of them not. Some are quite quick and other not. So the ink preparation could be more or less difficult. And then we have to look at the viscosity of the ink. So not all the techniques can be run for all the viscosity ink can have. And also they will give a thickness which is not the same for all of them. And last but not least, some of them are, well, most of them are compatible with roll-to-roll production, and others not. So I just want to quickly go through some concepts which are, I mean, can be important to understand what we are talking about later. So let's start with the surface tension and energy. So surface tension is something related to like liquids, and as you can see here, so molecules at the surface of a liquid will exercise a cohesive forces which resist to external forces trying to break the surface. Look at the image of this insect not going down in the water. So each molecule in the bulk is pulled equally in every direction by the other liquid molecules that are in the bulk. But the ones that are across the surface, they are not the forces acting on them, they're not counterbalanced by on this side. So the result is that a surface tension arises. And this is quite important for us to understand another concept that comes next, that is coming next, which is the wetting of a substrate. And the other concept is the surface energy of a substrate, which quantifies the disruption of the intermolecular bonds that occur on a surface. So let's keep these two terms in mind. I just put some surface tension values for the most common solvents that usually we deal with. So you can see like DI water has 72 dynes over centimeter of surface tension, and the most of the organic solvents that we usually use, they have like lower surface tension, which means that they usually have like better wettability than water, for example. So the substrate wetting is what dictates whether a coating, so an ink, a solution, will spread over the substrate or will retract from it. And what we look for is a substrate with a surface energy higher than the ink. So in that way, we will have a good transference spreading. To experimentally look at this characteristic, we usually measure the contact angle. So the angle which is formed between the ink and the substrate at their interfaces. And depending on the shape of this contact angle, well, we will have an idea if that solution that we are going to use is going to wet our substrate or not. This is a setup for the measurement of the contact angle. So it would be like this angle here. And another parameter that we have to have in mind for our decisions on the coating techniques that we are going to use and how we can modify our ink accordingly is the viscosity of the ink, which can be measured by a viscosimeter, or if the viscosity vary with the flow conditions by a rheometer. Right, so let's go back to our decisions. So now we kind of understand better the viscosity, but we also have to consider other aspects for in making our our devices. So first of all, have decide which substrate we are going to use. Have clear if we have an architecture where a mesoporous or a planar architecture. If our cells are have a PIN structure or a NIP structure, because this will determine which layer goes on top on which other. And also, and I would say mostly, we also need to consider the availability of the techniques in our lab, for example, or if we don't have any, the budget that we have available to buy a piece of equipment. So once we kind of make all these considerations, we also have to know which our target film is. So the thickness that we want to achieve, if we want a pattern or not, if we need to be careful about the registration, because, for example, we want to put a layer on top of the other, but just displaced of a tiny amount. And this could happen if we make modules, for example, by screen printing. We need to know the substrate roughness, either of the substrate itself or of the layer on top of which we are going to deposit the next one. And of course, we need to know the substrate surface energy that can be adjusted if it's not the right one via plasma or UV ozone treatment. Then we need to know our solution. So which solvents we are going to use, and if they are like toxic ones, as is usually the case of perovskite precursor solvents, we would need to set up an extraction. Then we would need to know the bonds, because that would affect either the crystallization of the perovskite layer, let's say, or the homogeneity of any other layer that we are going to. As I already said, we need to know how to understand in advance if there's an interaction with the underlying layers. Then look at the surface tension, make contact angle measurements if needed, and look at the viscosity and so on. Right, so at that point, once we have all this information, we can decide which coating or printing technique we want to use to replace the spin coating. So possibly the easiest one would be the blade coating, because it's a quite easy technique, because it's quite low cost, and it could be likely that many of you have up. So yeah, so you can see here like a deposition by blade coating or a perovskite layer. So how it works, so you just dispense some solution on the substrate, and you have a blade which is moved by like a motor which displaces it across the substrate, and the result is a wet film whose thickness is it depends on the concentration of the solid material in the ink and on the density of the material in the final. So as I was saying, the cost is similar to spin coating setups. The operational complexity is more or less the same, so it's not very difficult to use. But the advantage is that we waste less material. Also, it's compatible. The drawback is that we cannot obtain pattern layouts, so we'll just deposit the layer across all the surface, all the substrate. And this is quite a problem. The solvent evaporation rate is relatively slow. So we don't have that dynamic drying that I mentioned for the spin coating. And this is quite a problem, especially for the perovskite layers. Right, so just to prove this, I mean, to bring a practical example, we can see like two different videos. So you see here is the blade moving, and this is the perovskite film forming. This is in case of a higher temperature, while in this case is just a lower temperature. So the formation of the film will happen afterwards, and the morphology will be very different. So in here we have a kind of islands of perovskite, while in the lower temperature case, we have needle-like morphology, which is usually something that doesn't work. So as we can see here, at low temperature of the substrate, blade-coated perovskite film in complete cell will deliver very low performances, while if the substrate is heated over 100 degrees, then the morphology of the perovskite film would be much better. So the quality of the film will be much better, and as a consequence, the cells will deliver higher efficiencies. Right, so I need to do like these kind of parentheses here because it will help us understand all the following. So I just say that if we blade the perovskite layer and we leave it, dry at room temperature or at low temperature, we will have low quality films. So how can we improve the quality films? So let me thank our PhD student Farshad, who made a big part of the literature review of these things that I'm going to show you next. So we can adopt different strategies to improve the quality films, which are the post-processing, additive engineering, and solvent engineering. So the solvent engineering is something that I'm not going to go into much detail. So just an example here, if we use, instead of the usually employed DMF and DMSO, for example, the N-methyl 2-pyrrolidone, we will slow down the drying process. And this is because this solvent has a lower vapor pressure than DMF and DMSO. And similarly, you can adopt and use other solvents with lower vapor pressure than the typically employed ones. So just a spoiler alert, let's say, all I'm going to show now is taken from, blade coating examples, but it's valid for all the coating and printing techniques. So talking about post-processing, so we know that for spin coating films, there's this very effective method, which is the anti-solvent dripping, which helps a fast crystallization of the perovskite film by removing the solvents contained in the solution with these anti-solvents. So we usually have DMF and DMSO in our precursor solutions, and we use an anti-solvent which could be chlorobenzene or diethyl ether or toluene to remove the DMF DMSO mixture and get a crystalline high quality perovskite film in just a few seconds. So this is quite hard to get in coding and printing techniques. So for post-processing, we should adopt other methods. So the easiest one is just the heating. So we can use a hot plate or so a heating module to warm up the substrate even during the deposition, as we showed before. and in general, after the deposition to promote the conversion, the crystallization of the perovskite. Other methods are the gas flow, gas quenching, and the vacuum quenching as well. So to understand better the effect of post-processing and of all the other strategies, we need to understand, let's say, the dynamics of the crystal growth. So we can refer to the Lamerman model, which describe how the concentration changes with time, and how the film will form. So in a first step, when we deposit the solution, the precursor solution on a substrate, we will see an increase of the growing species in the solution, leading to a supersaturation. And at some point, this supersaturation degree would be higher than the minimum concentration for nucleation. And at that point, the nucleation will occur. And once we have nuclei spread all over our substrate, if the concentration goes down, we will have the growth stage where the nuclei will just grow by control of controlled by the growing species diffusion. So the key to high quality perovskite films is fast nucleation and slow crystal growth. And this is something that we can see in this example. So this is the speed of the airflow on the nitrogen blowing on top of the layer. And you see that as it increases, we have an increase of the nucleation, so more nuclei formed, and the grains are smaller, and the crystallization rate is also higher. So another strategy would be the addition of surfactants to reduce the surface tension or control the fluid dynamics. The addition of halide anion additives, the solution, to delay the crystallization of perovskite, hydrophobic groups, and functional groups in general. So what happens with them is that, so I'll show you here. So once we have like this L-alpha phosphatidyl-codeine surfactant, what happens is that we can obtain like a more uniform layer, and just by retarding the coming of the perovskite solute to this island of perovskite that forms across the layer. Sorry if I'm speeding up, but I'm afraid that I'm already like a half of my time. So another additive that has been studied is the ammonium chloride, and again is a compound that helps the crystallization by just delaying it. So if we don't use this ammonium chloride, the wet film will form rapidly, and some solvent will be trapped at the interface between the forming film and the substrate. And this will lead to voids in the perovskite layer, and then in poor performance of the cells. If we like by adding the ammonium chloride, then we'll retard the nucleation, and we'll obtain like more compact layers with larger grains, and in this case they demonstrated almost 16% on 43 centimeters square, where the substrate is flexible glass. Just another highlight on the current flexible PSC record, just to say that the big modules that they obtained, they were made by blade coating of the perovskite layer. And you can see that the performance achieved are quite impressive. So let's now talk about other printing techniques. So the screen printing is another quite common technique used in labs, where we have a mesh with a pattern. We have a squeege here that will pass across the mesh, applying a pressure, and this will force the ink through the mesh to give the desired pattern. So for the screen printing, we need a high viscosity and low volatility inks with isotropic behavior. So this is kind of limiting the use of this technique for perovskite cells in particular, because we all know that the perovskite solutions are quite, are liquid, they're not viscous at all. But it can be used to deposit other type of materials, perhaps mostly for glass-based perovskite solar cells. So it's largely used for metal oxide layer, for carbon pastes. But what we obtain are quite thick layers, and usually to remove all the additives that make the ink screen printable, so that add viscosity to the ink itself, high temperatures are required, which obviously are not compatible with flexible substrates. And yes, as a comment, if the screen printing is integrated in a roll-to-roll line, is called rotary screen printing. So the spray coating is another quite simple technique. I mean, in terms of setup, then there are like a lot of parameters to optimize. So how it works, we have say like a spray gun with a nozzle and a reservoir for the ink. The liquid is atomized in droplets. The droplets they just are transported from the nozzle to the substrate, and in this in-flight route that they go, they evaporate in parts. So the droplets that impact on the substrate then just coalesce together into a wet film, which is then dried. So we have in our lab an automated system. So you see, this is the noodles, and you can see like the solution, the ink being atomized and hitting the substrate. As I said, this is quite a more complex system than the manual one, but it works, I mean, following the same principle. It's just that we need to optimize like more parameters. So the good thing is that we can obtain homogeneous film on a very large substrate. So in this case, I'm showing something that we made within the Apolo project. So we spray coated the tin oxide layer, which is the ETL in our cells, on this 10 by 12.5 centimeters square. We kind of map the efficiency that we get from each of these devices, and we found that, well, it's quite homogeneous. And in the same way, we obtained modules, series interconnected modules, that deliver 12% of efficiency on 17 centimeters square and 10% on a larger active area of 22 centimeters square. Then the inkjet printing. So I guess that we are more or less all familiar with that, because I mean, there are a lot of inkjet printers in our offices, for example. So it's based on this digitally controlled process in which a piezoelectric stage ejects ink droplets that are electrically charged and accelerated towards the substrate. And then as a result, we get like the digital pattern that we can see on our screen reproduced with high resolution. Again, a lot of parameters involved in the definition of the final thickness. The inkjet printing is usually used with low viscosity inks with high surface tension, because we want, you know, the droplets to form between hitting the substrate. The good thing about the inkjet printing is that is a non-contact deposition technique that allows a precise control of the amount of the material deposited and, you know, the exact point where we want that ink delivered. There's no material waste, and it can create complex patterns. So I reported here a picture from a paper on OPB, just to show that, I mean, there's an absolutely freedom of shape with inkjet printing. So I would say that the only drawback, well, one of the drawbacks is that it's a really relatively slow technique, which could be limitation for coating on large areas. So yeah, just here an example of the inkjet printing applied to perovskite films. Again, you see that a lot of, let's say, strategies return in each technique. So if in this case as well, we have a substrate which is heated at different temperatures, from room temperature to 60 degrees. The choice of the solvent, in this case gamma butyrolactone, is because it's highly soluble for the perovskite precursors, and also prevents the clogging of the nozzle. And also, I'd like to show you this video. Sorry, I'll put it, okay, the volume down. So not sure, I mean, perhaps some of you already know this company, Polish company, Saule Technology. And they, I mean, since the beginning, they've been optimizing the inkjet printing for the perovskite. So, I mean, this video is already kind of not confirming what I just said about the limitation in the substrate dimensions, but obviously I'm thinking about, you know, research labs, not industrial facilities. So the slot die coating. This is another technique which is spreadly used in industry to deposit layers of different nature. So it's based on the formation of the meniscus between the coating head and the substrate, and this allows precise dispensing of the ink into the substrate and the deposition of a wet film. So the working principle is similar to the blade coating, but it's a little more complex in terms of fluid dynamics control, because we have to look at the flow rate, ink rheology, the coating speed. But the good, I mean, the big advantage is that a pre-metered technique, which means that the amount that solution we feed to the head is the amount of the solution that we are depositing on the substrate. So there's a very highly efficient material usage with low wastage of the materials. And also it allows a high level of precision, enabling fine control of thickness, even down to a few nanometers. And again, different pattern layouts can be obtained without limitation in length, and can be used for a broad range of ink viscosity. Just a spot on the theory behind to kind of make you realize that, I mean, it's quite complex. So there are, two deposition regimes characterized by different thickness behavior as a function of the coating speed. So there's an evaporative regime for low coating speed, where the time scales for the solvent evaporation and the coating velocity are comparable. So what happens is that the deposited film, it dries during the deposition. And then there's this, let's say, more desirable regime, which is the Landau-Levick regime, where the wet film is first dragged out before drying. So the coating velocity is higher, and it leads to the decoupling of the coating and the film drying. So the deposition parameters, which are a lot, you can see here some of them, must be optimized to prevent coating instabilities. So ideally, you want to be like in this stable deposition area, where you have a downstream meniscus and an upstream meniscus. Because in the other cases, you will have like failure mechanisms. So in this area here, for example, the downstream meniscus could break up and the film could just be discontinuous. And the other case, perhaps you will just float the substrate and lose the control on the thickness. Again, so these are examples of slot die coated perovskite layers, but you will see that some of the concepts that we presented earlier, they come back. So for example, we have in this case, this intra-additive approach where the deposition of the perovskite is done in 2 steps. So the first step we includes the deposition of a lead iodide solution dried by this air or nitrogen gas knife, sorry. And straight afterwards, there's another slot die coating step where methylammonium iodide solution is deposited and leads to the conversion of the lead iodide film. So by just having an unstable intermediate here, they have this very reactive lead iodide layer, which very quickly convert to perovskite when the methylammonium solution is deposited. And by just changing the perovskite composition from MAPI to double cation perovskite, and by changing the HTL, the transport layer from P3HT to PDOT, they got like an 11% on flexible substrate, and we are talking of slot die coating in a roll-to-roll line. In here, so we see here the effect of the blowing of the nitrogen as we already presented. In the second example, we'll see how by adding like a mediator, so changing the ink, the solution, the precursor solution, they obtain like a more porous lead iodide layer, which is then much more reactive when it's dipped in the methylammonium iodide solution, and the conversion of the perovskite is more effective without, any lead iodide residual. And just another example of, again, both using nitrogen knife and additives, in this case lead chloride. We see that the crystallinity and the quality of the perovskite film obtained by slot dye coating is improved. So without the additive, without the lead bromide, again, the crystallization is too fast, and it leaves behind some voids that are visible in the cross-section SEM. By adding the lead chloride, the crystallization is kind of delayed, and this helps to improve the quality of the perovskite films and leads to a more compact perovskite layer. Yeah, so I'm going to finish almost by just saying that all these techniques that I'm very briefly presented, they can be integrated in a roll-to-roll line. So you see each of them can be, made roll-to-roll compatible. And this is something that is very desirable for flexible substrate, obviously, but perhaps is more, for an R&D, at an industrial scale than for, all of us who work in academic research lab. And I want to leave you with this short video about, the main difference between the spin coating and a roll-to-roll process, just to, again, stress the why we need at some point to abandon the spin coating if we want to go towards larger areas. So we'll see that it takes a lot of time to do, this number of small devices. And also it needs a lot of solution, as I've been saying before, also for the case of the blade coating. And I find this very, clear, and perhaps I thought that is more direct than myself explaining and showing slides. So you see here, they have a small roll-to-roll equipment, and they are just charging a syringe, which will feed the slot die coater. And it's just, yeah, you can see here the film coming out nice and dark. And yeah, as they say that obviously they used a very low amount of solution, which they didn't waste, and the throughput of the production was much higher. You see the difference between the solution that has been used for one of them. Yeah, this is, you see, with a small amount of solution, they got like this very long strip of perovskite layer, right? So let me finish by thank my colleagues at CHOS, especially my supervisor, Professor Brunetti, and Farshad, who helped me preparing these slides. And obviously Apolo and the European Commission for funds. If you want any more information about the project, you can find it here. And if you want to follow our updates, we have a Twitter account. So thank you very much for your attention. I hope I've been, not so boring in presenting these, like in presenting the coding and printing technologies that can be applied to flexible substrates. So thank you very much.
Thank you very much, Francesca, for your very nice talk. I think that the students had the possibility to see more deeply what is the situation when you work with flexible devices and when you have in your hands the technology. So I think you have one question in the panel that it's what is or will be the cost per watt peak with both production methods.
Right. So this is a very interesting question, and I think I don't have, numbers to give you. Perhaps I can have a look, to the literature if anyone has already looked at this. And perhaps during the presentation of the Apollo project, we'll give some numbers about it. But, I would say that even if we don't have, I cannot give you by heart, numbers. The spin coding, for example, is not viable if you want to make a, production of modules or, square meters of perovskite solar cells. And the differences between the, the several coding and printing techniques, well, that would depend. I would say that there are several things that one has to consider when trying to estimate the cost for watt peak. So yeah, the short question is, the short answer is, I don't know. But I guess that I can find some, information for you to share. And I would take the opportunity to invite you all, because I had to summarize a lot of information in, a few slides. But since we are going to share the presentation, so please have a read at the, all the papers that I cited, because some of them are very nice reviews. And if you are, in a moment where you have to decide, perhaps your project deals with large area devices, or you just want to explore these coding and printing techniques, then yeah, I invite you to go more in depth. I'm sorry, the time was not enough for giving a lot of details, but I hope that I give you, some just inputs that you can just use as a guide to study more in depth this topic.
Okay, thank you, Francesca. As you say, I'm going to give more or less some data about the goals of Apollo project in terms of cost and of course the actual situation of the developments, but you need to take in account that when you are in a research stage of the technologies, it's very difficult to give an exact number about what is going to be the final cost of the technology, because you don't have optimized all the processing and all the things that you need to take in account in a production line. I think that I invite you also to assist to the talk to the Dr. Enrico Leonardi from Grace Sola, that is going to be, I think, at the end of the session of the morning, since he comes from the industrial part of the project and he's closer to this kind of data about the final number that we are going to have in a production line for flexible perovskite or even for commercial photovoltaics. So I think there is no more questions in the panel or even in the chat. As in the previous days, if someone have another question, you please write in the chat, and Francesca is going to try to answer in the chat box. Okay, so thank you again, Francesca, for your nice presentation. We are very on time, so according to the program, we're going to have a small break to have a little rest, and we are going to come back at 11:15 Central Time. So please, we will see in a few minutes.
Okay, thank you.
Hola, Ana. You have your microphone in off.
Yeah, now. Okay,
You are not in presentation mode.
okay, and you can see
You need to
come
go to
properly.
opción de visualización. Arriba.
Now.
Yeah. Right.
Okay, thank you.
Everything is okay. We're going to wait until the time of the break to start, okay?
Okay,
Thank you.
thank you.
Okay, I think that we are on time to start the game with our summer school, with the next talk of the day, of the session of the morning. So I'm going to present the next speaker, the Dr. Ana Maria Escobar from the Lake Technological Center in Spain. Dr. Ana Maria has a PhD in chemistry by the University of Barcelona, a master in advanced chemistry specialized in material science at the same university. During her PhD, he was involved at various national and international projects related with functionalized surface and conflict technologies. From the 2019, she works at LATAC at the surface treatment unit, participating in the drafting and execution of industrial, national, and international R&D projects related to the surface functionalization and modification on ceramics and polymers. Today, Dr. Ana Maria is going to talk about the consequence of the accumulation of dust in PV systems and one solution by anti-soiling coatings that are being developed within Apolo project in order to confer hydrophobic and simultaneously oleophobic behavior to the surface on flexible devices and consequently to reduce the soil deposition. Dr. Ana Maria, the floor is yours to start.
Okay, thank you, Anna, for your presentation. Thank you for everyone who's participating in this summer school. This is the content of my presentation for today. Firstly, I'm going to explain the soil problem and the possible solutions applied to solve
Anna, just a thing.
Yes.
We lost your audio for moments.
I don't know if I can enhance my. Now it's better or no?
No, we can hear you, but the problem is when you're speaking the phrase, the first part of the phrase is lost, and we all just listen the final part.
Okay. I start again. No problem. This is the content of my presentation. Firstly, I'm going to explain the soil problem and the possible solutions to reduce this dust accumulation. Then the specific solution in Apolo project with its practical goals, and finally the conclusion, the advantages versus disadvantages, and the conclusion. The soil deposition is one of the problems in the solar energy production market. The dust can reduce the conversion efficiency and, on the other hand, increase the OPEX of the plants. The OPEX is the operational expenditure. Because of it's mandatory clean the surfaces along the year. This operational cleanance is produced manually due to an increase of cost by the plants. The conversion efficiency of the commercial photovoltaic modules is as low as 20%, which is attributed to the reflection loss air module interface and the dust accumulation over the modules. As a result, improvement of solar modules has gained significant attention by the scientists all over the world. This improvement is largely focused on the development of functional coatings for solar panels. Moreover, dust accumulation is one of the major causes associated with lower energy outputs, And since power outputs has a strong positive correlation with incident solar irradiation, the layers of dust behave like a barrier for incoming. There are some publications about the relationship between dust and the reduction in power output in photovoltaic area. In photovoltaic area because it's the solar technology more industrialized. And when a dust deposition density increase to 22 grams per meter square, the reduction in power outputs can increase from 0 to 26%. Cleaning of solar panels after the installation on the roof of the house, industry, or plants is very difficult, as dust particles do not allow the solar radiation to enter in the panels properly, resulting reduced conversion efficiency of the panel and leading to increased charging duration of battery. Because of it, there is a need for the proper maintenance and cleaning of surfaces to keep working efficiently. To solve it, there are different solutions as cleaning robots, can be seen in the figure. This is a cleaning robot. Electrostatic precipitator is another possibility, and the self-cleaning and transparent code. In this technology, I focused on this technology because of the extensive range of applications from window glass cleaning, solar panel cleaning, cement or textiles. This technology received a great deal of attention during the late 20th century. And now numerous research work are going on around the world to develop highly efficient and durable self-cleaning coating surfaces with enhanced optical qualities. This figure shows the continuous growth of self-cleaning technologies from the number of papers published and the number of sites for the last year. Apart from the wide range of applications, this technology also offers various benefits, which include the reduction in maintenance costs, the elimination of tedious manual effort, and also reduction in the time spent in cleaning work. Regarding cleaning robots, there are some of it that has been tested, as can be seen in this figure. This cleaning robot has been tested for extreme conditions in Chile, in Atacama. Has been capable to semi-autonomous cleaning with low water consumption or without it. But this is a prototype and its price is high. The automatic wiper-based cleaning can incorporate a rubber and a water pot for the spray the water with additives. The process is exactly like a vehicle glass cleaning and requires an automatic mechanism to operate and complete the task. In the case of the electrostatic precipitator, considering the impacts of different cleaning methods, the mechanical damage, scratch, and scars like marks, the electrostatic precipitator works with non-contact mechanisms. It cleans efficiently and protects the top surface of the panel or the surface without any physical contact. An electrostatic precipitator is a filtration device that removes thin dust particles from the surface using the force of an induced electrostatic charge. The mechanism consists of the electrodes, which are charged suitable as shown in the figure, and the dust particles are accumulated at the positive electrode after being attacked. In this way, a non-contact dust cleaning technique helps in improving the efficiency of solar panel. Currently, that this technology is being developed and is not marketed. My presentation is focused in self-cleaning coatings as the best anti-dust solution. Many technologies existing in today's world have been derived from nature, and self-cleaning is one of them. Many surfaces in nature exhibit self-cleaning. The wings of butterflies, the leaves of plants, such as the cabbage or the lotus, the rose plant, are a few examples. Self-cleaning coatings are broadly classified in two major categories, hydrophilic and hydrophobic. Both of the categories clean themselves by the action of water. In a hydrophilic coating, the water is made to spread, sheeting of weight of water over the surface, which carries away the dirt and other impurities. Whereas in the hydrophobic technique, the water droplets slide and roll over the surfaces, thereby cleaning them. The self-cleaning phenomenon is related to the surface contact. It's the angle formed at the three-phase boundary, the solid, the liquid, and the vapor between the surface of the liquid drop to the surface of the solid. In general, if the contact angle is more than 90 degrees, the surface is defined as a hydrophobic surface. Similarly, a surface with a water contact angle approaching 0 or 10 degrees is classified as hydrophilic, and a surface with a contact angle more than 150 degrees is usually categorized as ultra or super hydrophobic. In Apolo project, we are developing self-cleaning and super hydrophobic coatings onto flexibles. And also the coating should be produced by easy and scalable. First of all, is what is a hydrophobic surface or a super hydrophobic. The development of self-cleaning materials and engineered artificial surfaces is inspired by the leaves of lotus plant. This is the iconic surface of super hydrophobic behavior, on which water rolls off to spherical droplets run away from the surface that is commonly known as lotus effect. As the name suggests, such materials can easily be cleaned by a stream of natural water, such as rainfall, which in turn significantly reduce the routine maintenance. Superhydrophobicity of lotus weave was explained due to the raw hierarchical structure by a micrometric, can be seen in this scanning electron microscope, the nanometric roughness, and in addition to the hydrophobic wax layer on the leaf surface that promotes a reduction in the surface tension. At very high magnifications shows that nanorods of wax are randomly distributed on the surface. This double roughness is hierarchical structure that is the key of the superhydrophobicity. So this behavior is not shown without the wax or another component with low surface tension. A hydrophobic surface is characterized by its water contact angle, as can be said before. For a flat surface, a static contact angle measurement is close to the Jones angle. Rather than flat surfaces, Wenzel's model and Cassie Baxter's model bring a new guideline for raw surface studies. The behavior of water droplets based on Wenzel's model and Cassie-Baxter model can be seen in this figure. In the case of Cassie-Baxter regime, the water suspends above the aspidity because the R fraction are between the peaks. In this case, if your system is based in a Cassie-Baxter model, your system is non-sticky, is a non-sticky model, the Lotus leaf. But in the case of Wenzel's model, the water slightly imparts the asperities. In this case, if your system is based in a Wenzel model, your system is sticky. In this case, you have a system similar than the rose petal. The water droplet is shows a water contact angle more than 90 degrees, but if you move the rose, the water maintains sticky inspired by the superhydrophobic properties exhibited by nature, researchers around the world start working on developing technologies to produce surfaces with extremely low surface energy and also to control the morphology of the surface on a micron and a nanometer scale. This idea of controlling surface morphology opens many possibilities for developing a variety of engineering techniques to produce hydrophobic and superhydrophobic surfaces can be broadly classified into two categories. First, making a rough surface from a low surface energy material, or modifying a raw surface with a material with low surface energy. The electrochemical polymerization method is one of the most promising methods because it proposes a facile control over the surface feature and provides an easy way to create various morphologies. Tubes, needles, dendrites, as can be seen in figure, fibers, sheets. This figure corresponds to Jiang's work, in which inducing long-chain fatty acids to produce micro and nanoscale hierarchical structure copper mesh that exhibit superhydrophobicity and superoleophilicity in this case. These superhydrophobic 3D porous copper films were fabricated by using hydrogen bubbles as the dynamic template for metal electrodeposition. The magnified semi-image in this small figure shows the porous structure with numerous dendrites in different directions, forming a strong field. Very similar to the lotus polymer self-assembly and layer by layer assembly techniques are based on sequential absorption of a substrate in solutions of oppositely charged components. These techniques continues to be the most popular and well-established methods for the formation of multi-layer thin films. They are inexpensive techniques in which micro and nanoscale superhydrophobic structures can be easily fabricated with finely controlled surface morphologies. This figure corresponds to the work of Lee et al., and they synthesize an adjustable dual size roughness surface consisting of raspberry-like particles by the assembly of silica. Electrospinning is one of the simplest and most useful techniques to yield continuous polymeric strings with diameters lying in the range of a few micrometers to nanometers that can be accumulated to develop surfaces having characteristic surface roughness. By this method, in this case, in the case of the figure, cellulose acetate fibers were made to form a unitary structure that is similar to that of ramilli. These fibers show a smooth surface, showing a small hydrophobicity. After a treatment with fluoralkyl silan modification, this cellulose acetate exhibit a water contact angle of 140 degrees, very close to a superhydrophobic. Another group of technologies is templates and modeling. One of them is the lithography. Lithography is a conventional technique used to create micro and nano patterns. Different lithographic techniques that are in practice are photolithography, electron beam lithography, nanosphere lithography, and this figure corresponds to the work of Martinez et al. They employ the technique of electron beam lithography and plasma etching to produce an array of nanopits and nanopillars on the surface of the material. And when this surface in the next step was hydrophobized with octadecylchlorosilan, it exhibited superhydrophobic properties with a great water contact angle of 164 degrees. In the case of plasma techniques, as plasma etching processes or CVD or chemical vapor deposition, they have been extensively used with polymers to fabricate different functional surfaces with a lot of different morphologies. In this case, this figure corresponds to a superhydrophobic polymethyl methacrylate surface under low pressure conditions in high density plasma reactor. This figure is not a scanning electron microscope image because it's the AFM topography. And another polymeric technology used for cleaning coatings is the technique of presentation of the product. This figure corresponds a surface fabricated by electrochemical deposition. This technique is widely used to develop biomimetic surfaces because it's a versatile technique to prepare this dual roughness. And in this case, in the case of the figure, a galvanic deposition on metals to deposit metallic salts and polymer, polymer, which result in the formation of a superhydrophobic surface with a great water contact angle of 170 degrees. This type of surfaces can effortlessly float on a water surface, similar or because of similar to the pond skater, this animal. And finally, there are a lot of technologies, but in this case, I'd like to explain you an example of salt gel, because salt gel method can be employed in the fabrication of these superhydrophobic surfaces in all kinds of solid substrates. This figure corresponds to Hikita work. They prepare salt gel films by hydrolysis and condensation of epoxy-silan. This is the first step of salt gel method. And colloidal silica and fluoroalkylsilan were used to control the surface energy and the roughness of the film. Optimizing the amount of colloidal silica and the fluoroalkylsilan in the film, a superhydrophobic and a very transparent surface has been produced. The superhydrophobic coatings, films, surfaces exhibit tremendous applications in different sectors, especially in energy-related fields, because superhydrophobicity and self-cleaning effect has another properties very close to them. Some potential application of superhydrophobic surfaces as anti-corrosion, anti-fizzing, anti-frosting, anti-icing for photovoltaic cells, for ships, for aeroplanes, anti-friction for submarines, as can be in Apolo project, the anti-soiling coating is working at the external layer. So our first rule is not disturb to the cell efficiency. As consequence, the coating has to show a high anti-soiling effect with very high transparency, and also the coating has to be deposited over this last layer of the perovskite cell. This is the gas barrier. They have knowledge in different anti-soiling technologies. One of them is a combined strategy of plasma activation of the substrate and another step of diagramming. In this case, this figure shows 3 different images of water contact anchors. First of all, the substrate at the beginning of the process, in this case is glass, but this technology can be applied to solar glass or polyurethane, PMMA, polycarbonate, Teflon. This surface shows a water contact angle of 50 degrees. And after a plasma activation in this case by atmospheric plasma, the surface wettability has been improved. And in this case, in the figure, you can see that the water droplet only here because the water contact angle is near to 5 degrees. After the high hydrophobicity has been promoted by a deep coating step with different functional precursors, and in this case, the water contact angle is 120. Another anti-soiling technology from that is silica coating drafting. This is a 2-step process with an inorganic coating with silica in order to confer a correct roughness, and immediately after a grafting process with a functional precursor in order to confer with this functional precursor to confer a low surface. In this case, it's possible to need an activation of the coated surface before the functional precursor application in order to improve its bettability. Finally, other technology from LATAT is a hydrophobic and bio-based coating. Bio-based coatings has a strong interest in the last years because its key precursors are not petroleum products. In this case, we use fatty acids from oil plants with a suitable solvent and produce a super hydrophobic polyamide. The evaluation of these three anti-soiling technologies are summarized in this table. The obtained transparency of the fast coating corresponding to the grafting, the first technology, the fast coating, and the fast silica coating corresponding to the second approach is very high. But in the case of the fatty acid coating, the transparency is low. The expected durability of these three technologies are low medium. There are many efforts to improve this durability, and only fatty acid is considered eco-friendly, but the obtained surface is not oleophobic. That is very important because in Apolo project, the devices will be located into buildings, in cities or industrial plants, but this is significant because the dust composition is not the same than in natural environment. And as consequence, fatty acid coating has been discarded to Apolo project. On the other hand, the bettability characterization in all of the steps of the process is very important because it's a key factor to obtain a good coating. In the case of lack of bettability, as for example, if your substrate is Teflon, an activation process of plasma by low pressure plasma or by atmospheric plasma can be a good solution. There are different techniques to characterize the bettability. And the technique more easy and only qualitative is the ink test. The ink test is applied quickly to the surface using the integrated brush of the bottle. Each ink has a known surface tension, and it's recommended to start with a ink with a high surface tension. Such as 72 millimeters per meter, similar to the water surface tension that is 74 millimeters per meter, directly on the surface, can be seen in these figures. If the brush stroke edges are stable for 2 seconds, the surface is easily bettable. Then the surface tension of your substrate is at least equal to the value of the test ink. If the brush strokes of the test ink the next lower test ink should be used. This way, you are gradually approaching the surface tension value, and finally, the surface tension of your surface is equal to the value of the last test ink used that show good weighting for at least to 5 seconds. Although the maximum measurement error of this is 2 millimeters per meter. Another equipment to measure wettability and the surface tension is the tensiometer. You need to have a surface with high wettability to obtain an homogeneous film fitted. The surface wettability is related to its surface tension, and remember that high wettability shows high surface tension values and a lower water contact. In this case, this method, the tensiometer, is quantitative and establishes a relationship between surface tension, the force, and the contact angle. Finally, the goniometer is the equipment that provides results more faster than tensiometer. The anti-soiling effect of the coated samples in Apolo has been characterized by this goniometer. In this case, you can measure the water contact angle.
No. Hi, Monica.
You've been very busy.
Oh, sorry.
Yes. So I'm actually on this Apollo summer school.
Bojan. Bojan.
So not
You
much.
please
Can you-
switch off your microphone.
Yes. Okay. Thank you, Bojan. Okay. In the goniometer, you can measure the water contact angle, measure it since the Young's equation. Between in this Young's equation, the contact angle shows a relationship between the interface, interfacial tension between the three different phases: interfacial liquid vapor, the solid liquid vapor, and the solid vapor. Intermodynamic equilibrium state. In this case, the program of the goniometer measures the dimensions of the droplet and the angle formed between droplet and surface. But this is the static contact, the most usual measure to speak of anti-soiling or self-cleaning. By a dynamic contact angle and a rolling contact angle can be also measured with this. The anti-soiling effect has been evaluated by a soiling test with normalized Arizona sand. This setup to run anti-soiling tests in Leitad has been manufactured. It consists in a sample support where the samples can be fixed at different inclinations from the baseline. This is very important because to test the real conditions of the device, because photovoltaic panels have an inclination angle very different to the perovskite device of Apolo, for example. And also a protective PMA box to keep sand around the samples in the test. And an electronic balance is used for weighing the samples before and after the sand deposition. The soiling test is carried out simultaneously over a reference and a sample. In this case, this is the substrate, an uncoated sample, and this is the coated samples, and the same in this case. the coated sample and the reference. The reduction of sun deposited of each set of samples is obtained by the following calculation. You have the weight of your substrate and of your coated samples before the anti-soiling test, and you can measure the weight of your substrate and of your coated samples with the deposited sun without cleaning, and you have your sun deposited in your reference and in your sample, and the difference allow to calculate the reduction of sun deposited. No, if you have a coated sample with a sticky property, you don't have a reduction because you have an increase in the sun deposition, respecting the substance. As can be seen in the figure, the coated samples show a good aspect in comparison with the substrates. They are fully covered by the dust. And finally, another characterization of the anti-soiling coating is the agent test. Samples were subjected to different agent tests under simulated conditions. The tests were defined from the standard from TV, the terrestrial photovoltaic modules, design and qualification and type approval, used for the commercialization of PV modules. The chosen test can be selected considering the most extended test for the validation materials in PV modules, and the conditions of the test were defined to demonstrate the feasibility of the selected stack of the PV module use and considering its particular use and expected lifetime. The most critical tests for polymeric layers and adhesives of the standard are UV test, the thermal cycling test, and damp heat test. The UV test was performed using a climatic chamber equipped with a metal halide with high ultraviolet light content, and the damp heat and thermal cycling test were performed in a smaller model of the same type without illumination. Regarding the Apolo solutions and the selected technologies have been firstly a bottom-up strategy in which the growth of the next film starts at the surface of the gas barrier field. There is a two-step process with a spray deposition of a silicon blend, and after an immersion process of a functional. Two different sizes of silica nanoparticles have been tested, and the results show that the dual roughness promotes a better superhydrophobicity, and different relationship between particles, between silica nanoparticles and binder have been tested also with different relations, 1:1 or 2:1, 3:1. I think that 5:1. More particles promotes an elevated superhydrophobicity, but these particles increase the scattering and the transparency has been reduced. On the other hand, different functional precursors have been tested, and after it, the reaction parameters have been optimized, the concentration, the the reaction time, the temperature, and these precursors are difficult to work because are very reactive to water, and it's necessary to control the atmosphere. On the other hand, the polymeric gas barrier film has been treated by low pressure plasma in order to activate its surface, increasing its wettability, and immediately after it, a deep coating process with a functional precursor with done to enhance its hydrophobicity. In this case, the plasma activation parameters have been optimized to increase the wettability of two different gas barrier films because the different gas barrier film implies different wettability and different solutions. Two different anti-soiling commercial products has been compared with the developed in Apolo. These commercial products are applied for PV, for photovoltaic area, but in this case, the anti-soiling solutions of Apolo shows better superhydrophobicity onto gas barrier film than the anti-soiling products. And in the same, the other strategy, different functional precursors have been tested, and is a little difficult to work. At the moment, our coatings development is focused to optimize the best liquid repellency with the best transparency. The strategy bottom-up promotes super-amphiphobia gas barrier film, but the transmittance losses are a little more than 4%. This is our limitation. This 4% of losses. The strategy top-down promotes superamphiphobicity onto solar glass, but only amphiphobicity onto gas barrier. The best results of self-cleaning effect onto gas barrier film has been 120 degrees. This is only major coating thickness reduce transmittance, can increase a little the water contact angle, but reduce transmittance. And the increase of roughness produce the same effect in the transmittance. And the functional precursors are very difficult to work with room conditions. Finally, this is the conclusions of the presentation. The efficiency of solar energy production is being reduced due to the reflection losses and the soiling deposition. Self-cleaning coatings is a good solution to reduce soiling problems. Amphiphobicity is needed to obtain a global anti-soiling behavior, not only hydrophobicity. The anti-soiling coatings of Apollo project shows a high reduction of sand deposition in terms of 30% of reduction of sand deposition, respecting the substrate. And I finish my presentation. Thank you all the participants, and if you can ask one question or more.
Thank you very much to the Dr. Ana Maria for her interesting talk. Well, you can see that the problems that the technology can suffer are not only related with the devices itself. When we have the technology in operation conditions, we have many things that can have consequence in the global energy production and of PV plant. So thank you very much, Dr. Anna, to introduce the students to this kind of problems that face photovoltaic technology and other technologies also that are in outdoor conditions. I cannot see any question now in the chat or in the question panel. I don't know if everyone has something to add or to ask to Dr. Anna. I think I cannot see anything. So Anna, if you can state for a few minutes, just in case someone posts a question and you can answer by the chat.
Of course. Thank you.
Okay. So thank you again for your presentation.
Thank you.
Okay, so I think we can start with the next speaker. It's Dr. Enrico Leonardi from Brazil Solar, Italy. Dr. Enrico joined to GSI in 2009 as Area of Science, first managing the research project lines, and then latterly becoming the technical manager of the company in projects and equipment manager for the group with a global market responsibility. Enrico has a Bachelor of Science degree in electronic engineering from Tor Vergata University, a Master in Science degree in electronic engineering high frequency from Tor Vergata University also, and a doctorate from Tor Vergata University in the field of microelectronics and telecommunications. Dr. Enrico has an extensive expertise on the DICE solar cells and in perovskite technologies. He worked intensively on DCC and perovskite scale-up, development of perovskite solar cells, DICE solar cells and perovskite encapsulation and lamination, and of course, DICE solar cells and perovskite panel realization. Extensive background in DICE solar cells and perovskite technology, scale-out, project management, and problem solving. So today, Dr. Enrico is going to focus in flexible perovskite solar modules on metal substrates as a perspective for industrialization. It's very nice to have the opportunity to have the industry participating in this summer school, since up to now, all tasks were done by researchers and scientific community. So this is the time to see what is the real vision of the technologies, and of course learn about the experience that the industry is taking with this novel technology and promising technologies. So Dr. Enrique, thank you very much for being here, and the floor is yours.
Okay, thank you, Anna. Hello to everybody. Let's share my screen. Okay, so you can see my screen in the presentation mode.
Yes, Enrique, we can.
Okay. Hello to everybody. Thank you, Anna, for your nice introduction. As said, I am Dr. Enrico Leonardi from Grezzer Solar Italia. It's a member. Grezzer Solar is a member of the Grezzer Energy Group. That is a worldwide group based in Australia. And the mission of our company, obviously, is to commercialize the perovskite technology as soon as possible. It's, during my talk, I will, let's say, will be focused on research part that we are carrying on inside the Apolo project. But also I will give you also an overview of the point of view of the industries on the new technologies and show you the main bottlenecks that has to overcome before to scale up to an industrial level. And then I will finally introduce you the so-called levelized cost of energy. That is a fundamental parameter for industries, for investors, in order to evaluate the goodness and to compare different heterogenic power generator technologies. Okay, let's start with just a very brief introduction to what is scientific research in my mind. Let's say, to summarize the meaning of so wide word, it's very hard, but in my mind, scientific research is purely the future. It's without it, the human being will be die out very quickly. So it's important to dedicate time, efforts, and of course money in order to improve the research and to find something that has to improve the conditions and solve problems that the older community has on inside and around the world. Let's say the scientific research for me is like a large universe full of things and interesting topics. Of course, you have to find something that is of your interest, and you can see that you have to find your spot, let's say. And when you think that you find something, probably you have to go more deeply inside the technology. And when you reach your, let's say, solar system, where is your comfort zone, but you will discover that probably you have to go deeply inside the technology and check where is the material, the subjects that you want to study and doing research on. And when you finally think you have found your spot, probably you have to go a little bit outside and find something that would be your activity, that probably will be a tiny little part of the technology that you want to study. So to find the right subjects to study, it's pretty hard, but it may give you a lot of satisfactions. Let's pass to the concept of the flexible perovskite solar cells. The flexible perovskite has a potential huge market. The application may vary a lot, really a lot, and can be, for example, installed on the new generation drones or on consumable things, wearable electronics, jackets, or even can be used for from architects to improve the layout, the design of new constructions and make them more appeal for the public, let's say. This is a short history about the improvement that have been done during the past years on the flexible perovskite. Everything, let's say, we can say that started around 2013 with low efficiency devices, and very quickly in 7-8 years, the efficiency skyscraper up to about 21% on flexible substrate. That everybody that works on such kind of substrates knows that it's a little bit more trickier than to work with rigid substrates. There are several different flexibles, let's say, substrates. One is flexible glasses. Then there are the polymeric ones that are PET or PN ITO, that depending on the temperature that you want to use during sintering, You can use PT for lower one, PN for a little higher sintering temperature, but anyhow, they have to be lower than 180 degrees during sintering temperatures. Then there is polyamide substrates that allow you to even rise a little bit more the temperature during sintering. And then we can move to metal foils that give you the larger opportunity to even use high temperature processes and materials that needs to be treated with high temperature. Let's say high temperature, incomparable with, for example, 400 degrees, 450 degrees, for example. And then the new interesting, let's say, type of materials are nanocellulose papers that are starting to come out on the research with interesting applications where the research is at the beginning. So let's go more deeper in the discussion about why to use metal substrates rather than plastic or flexible glasses or polyamide substrates. Let's say metal has basically high electrical conductance, has a compatibility with the high temperature, is a very, very low rate. It's perfect barrier against water permeation and gas permeation. It has, depending on the materials, on the metals, there are some that have excellent resistance against corrosion and have obviously some, depending on the materials, excellent relation of strength to weight. They are, in many cases, more compatible for building integration, but there is always a but. Let's say, being metal substrate or completely opaque to the light, the metal-based perovskite solar cells needs to be illuminated from the back, so from the back electrode. This will imply some, let's say, problems in terms of transmission of the light, and this will reduce a little bit the efficiency respect to polymeric substrates, and but you have always to find a trade-off between performances and applications, let's say. So far, the best cells results on metal substrate solar cells are the ones shown in the slide. But we have to say that so far, all the experiments done around the scientific communities were published, at least, are all focused on small-size solar cells. Nobody worked in extensive way on modules, and it is on module size, and it is what we are doing in the Apolo project. We are developing module size metal-based solar cells, perovskite solar cells. Let's say after the cell, we have to move to scale up, to move to from small cells to module size, and then possibly to large area devices. And it is something that if you want to move out from the lab, it is something that you have always to take in mind that one time or the other, you have to get larger. So if the natural evolution is to arrive to something that can be integrated in different, let's say, buildings or construction, if you want to go on the building integration applications, you can remain even small in dimensions in the case you want to go to the, for example, IoT electronics, wearable electronics, and so on. But both applications has really good potential in terms of market. So the transition from the laboratory to industry imply that you have to use compatible deposition techniques to with the industrial environment, let's say, and this is something that you have to take in consideration if you want to think a little bit from an industrial point of view. When you remain inside a research lab, doesn't mind if you use if you work inside glow box, if you use evaporators or a spin coater for deposition. If you want to move up and get larger and go to industrial environment, unfortunately, the greatest part of the deposition techniques that are commonly used inside labs, research labs, are not compatible. So you have to probably move to row, sheet, screen printing in order to have a larger production, get larger. Then you have to consider also that you have to pattern your design in order, when you get larger, in order to reduce the series resistance of your device. So let's say, depending whatever configuration you use, that is on polymeric substrate or on metal substrate, you are limited by series resistance due to the electrodes. Okay, so in order to reduce the series resistance introduced by limitation from electrodes, you have to consider the patterning in order to have, for example, series connection on the same substrate. Historically, there are four main methodologies in order to make the series connections on the same substrate. They are basic: the photolithography, the mechanical scribing, shadow mask, and last but not the least, the laser scribing. The laser scribing is the system that allow you to be more precise, let's say, and give you the larger active areas and smaller depth areas as possible. And the fine-tuning of the laser scribing system will allow you to have a low series resistance as possible. Sorry. So in the case of metal substrate, there is an addition in the case you want to use a module configuration, a series connections of several stripes. You have to introduce an insulator materials between the metal foil, the metal substrate, and the rest of your module. Then after the deposition of the insulator layer and all the stack of your cell, then you have to laser pattern in order to create the series connection among the stripes. And then this is shown more or less the direction of the current flow in order to have an idea of what you have. The active area, unfortunately, cannot be too large in order to not introduce too high series resistance. So you have to find a compromise between active area of the single stripe cell and the series resistance of the substrate. And obviously, you want to reduce at the minimum the data area dimension in order to maximize the aperture rate, the active area of all your model. The key point of the metal substrates is to have a very, very good planarization of the metal substrate, let's say. This because all the layers in the perovskite technology are very, very thin. We are speaking about hundreds of nanometers. The standard roughness of metal substrate, to let you understand, even if you touch them, you feel that they are very smooth. The standard roughness is around 150, 200 micrometers roughness. So you can imagine that you can easily understand that this roughness is too much. And it's practically impossible to deposit a perovskite solar cell on without having shorts or a very, very poor efficiency. So there are basically two approaches that are done to planarize metal substrate. The first one is to deposit a planarization layer that may be done with several materials that of course has to be compatible both with metal and with the active layers of your solar cells. And then there is also a mechanical polishing. The mechanical polishing is the one that allow you to have the smoothest surface. You can reach even roughness below 20 nanometers, and you will have the so-called mirror-like aspect of your metal substrate. Very, very planarized metal substrate are let's say, can be used like mirrors in the houses, for example. So then, after having introduced quickly the approach that we are using to realize the metal-based perovskite solar cells, the bottlenecks said are the planarization of the substrate and to find the semi-transparent backed electrodes that is efficient in terms of conductivity, but has not to be too much opaque in order to not reduce too much the light that has to be absorbed from your cell. Let's move to let's say a more industrial point of view. When you speak about industries, unfortunately, all the possibilities that you have in the labs in order to realize your devices, to make layers and layers, reduce really a lot. So in order to reach the production, a visual thing, a visual object that gives the idea of the path from lab to industry is a funnel, let's say a common funnel, where each chain represents a hot topic for the industries that needs to be addressed in order to have a commercial product, and this product has to be challenging on the market. You can have a very good device, a very good product, but if the final price is too high, for example, it will not arrive. You will not have success in the market. Let's go to analyze the main, let's say, bottlenecks that we see in the industry. The technology that you want to use has to be eco-friendly. Let's say this is something that in the past year nobody cared, but recently in the last, let's say, 5, even 10 years, it's something that it's becoming more and more important year by year. The materials availability, of course, and the related cost. There's no sense to use rare materials or materials that you know that in a very short time that will be expired and will not be possible to use anymore, or if they are dangerous, for example. But this is something that is correlated with the eco-friendly technology. Then another really bottleneck is the deposition techniques. As anticipated before, you cannot use the deposition techniques that you want. And obviously, these deposition techniques are to be compatible with facility environment. For example, to consider to work inside a glow box like inert atmosphere inside an industry is completely, it's nearly crazy. It will be really impractical. And something that can be easily done is to work in dry air condition. But even if to work in clean, like the white chambers, it's something really expensive and really hard to do in an industrial environment. Another point is the production cost. Always money. When you are looking, unfortunately, from an industrial point of view, money is your keyword. You have only to take in consideration cost, production cost, materials cost, environmental cost, deposition, pieces of equipment cost, and so on. Then, obviously, you need to have a well-performing device. Otherwise, you will not be challenging on the market. And finally, obviously, your device has to have a good lifetime. And one of the most important thing is that the payback time of your investment has to be compatible with your business plan. It is something that is really important, and only at the end, you probably may have something that is a commercial device. Let's go to analyze each one of the chain that we introduced on the previous slide. The eco-friendly technology. What does it mean, eco-friendly technology? There are very nice statements that you can find around the web about the eco-friendly technology. But basically, it's something that reduces at the minimum the impact in terms of pollution, in terms of raw materials, in terms of human beings, in terms of manpower, the world, let's say. So, and as said, year by year, this is becoming a more and more important aspect that sometimes, if your technology is not considered eco-friendly, will prevent you to obtain funding from public companies or from EU, for example, of local governments. But anyway, even if it is becoming a hot topic and everybody around the world speaks about pollution and environmental impacts, you will always find around the world people that don't care about the pollutioning or don't care about or don't believe in climate change. So I said that is a very hot topic. To give you an idea, and it is something that the industries looks very well around the world, like European Community declared that the EU countries has to become carbon neutral, climate neutral by 2050. This is something that 2050 seems to be so far like a date, but it's not so far because a lot of work has to be done. And luckily, European Community is putting a lot of money on this aspect. And it is like, for example, the Green Deal. It will allow to have a lot of fundings in order to improve the technologies and push green technologies. not only the European community makes important statements, also US government said that in 2030 they want to reduce up to 50%, at least 50% of their pollutioning respect to what they are doing today. And also China. In the last years, they always said that they will reach their peak emission by 2030, but never said anything else. But recently, President Xi Jinping announced that China, for the first time, said that by 2060, they aim to be carbon neutral. It is important because these three actors are the ones around the market that put the greatest part of the funding that may be used from research entities or even from private companies in order to achieve something good for commercialization and to push green technologies to reach industrialization. The second important aspect that you have to take in consideration when you want to pass to industry, to production, is the raw materials. Let's say, no sense if you want to go on large production to still use rare materials. Unfortunately, rare materials are in many cases based on countries that are, let's say, not stable in terms of politics, and today they are friend, tomorrow they be your worst enemy. So it is important to move out from rare materials. European community, like all other countries, are pushing a lot to move out from these materials, and new technology, new projects are always more and more required to use abundant and low-cost materials. Let's say, in the case you will be the greatest genius in the world and you will find something incredible, and you say that, for example, you have invented a solar cell that has a 70% power conversion efficiency, and you have to be also a good advertiser and good speaker, you will be surrounded by possible investors that see the possibility to make a lot of money with your inventions. But if the same person will then say that, for example, he needs very rare materials that probably cannot be achieved, and they are very, very expensive to be achieved, then you will be see all the investors disappear very, very quickly as they arrived. So take always this in consideration when you want to move from lab to industry. Let's say, even if you are using very rare materials, you obtain very incredible results. Don't worry, because there will always space on very nice publication, on very high impact factor papers, let's say, and always looks around the corner, because you can find, even if you have to go on an asteroid, let's say, to find your materials, you can find always someone that can put some money on this adventure, let's say. Let's move on and analyze the deposition techniques and facility cost. I said deposition techniques has to be compatible with the industrial environments. The main are sheet-to-sheet, roll-to-roll, slot dyeing, jet, spray coating. Recently also atomic layer deposition and sputtering are starting to become compatible with industrial environment, something that in 10 years ago, 15 years ago, it was not possible. So even new deposition techniques are entering in industrial, the industries. But I think that has to be taken in consideration is also the cost of such equipments. Obviously, it's always a trade-off of what you can obtain and the payback time. Obviously, longer is the payback time, lower is the possibility to obtain funding by investors, let's say. The production cost is another really important key parameters. It includes manpower, maintenance of your facility, and also cost of the facility. And it is not marginal. Let's say it is sometimes it is the main responsible for the final product cost. It is important to take this in consideration. And obviously, it's trivial to say, but the production cost has to be kept as low as possible. These are, unfortunately, pushed in the last 50, 60 years, all the major companies to move the production side to countries where the manpower, the production cost is very low. But at the same time, the human rights are not considered, like China, Cambodia, Myanmar, Vietnam, and so on. So we have to also, if you have some ethics, and you have to always to take in consideration that when you want to go very low in costs, probably you have to accept also that some production is done in places where human rights are not, let's say, very good. Let's go on. Another chain is the performance. Obviously, in the case of PV cells, we are speaking about PV technologies, has to be higher possible. That's to be good for low light, in theory, for high light applications, and the performance may significantly reduce the payback time. It's trivial to say. Yes, I understand, but I can say that it's not always like this. There are specific areas where these statements are not really true. The payback time is something really important from an industrial point of view, especially on the side of the investors, so the people that puts money to realize the facility. To let you understand, to open a production line for PV cells imply investments of more than 100 million euros just for a production line. For a medium-sized pilot line, we are speaking about cost around 10 million, 20 million euros for a medium-sized pilot line. Just to prove that your concept is scalable to reach production. So nobody will give you money in the case if they don't see the possibility to make profit out of it in the future. So even if you have a very nice device, in this case, speaking about PV technologies with a super power conversion efficiency, but the payback time is too long, or worse, it will be never reached inside, you will never reach the payback time inside the lifetime, within the lifetime of your device, probably you will never, your product will never become commercial. Also this, it's not always true, I have to say, because if the technology is considered strategic for a country in some ways or whatever, probably you can find the government will finance the technology, even if it is not, they cannot make profit on it. But these cases are very rare, let's say. So the payback time needs to be as short as possible. So what to say about lifetime and payback time? Also, this it seems to be trivial to say, but it is lifetime has to be longer as possible. and it is, but also this is not really true, always true. I want to make you an example. Let's say if you want to integrate a PV cell inside a device that has only, for example, 5 years lifetime, but there are devices that have even shorter lifetime, like the IoT devices, it's useless to integrate a PV cells that has 20 years lifetime. Why? Because generally speaking, longer lifetime devices, especially for PV cells, imply more expensive materials, longer R&D, more expensive manufacturing steps and procedures, expensive encapsulation materials, and all these aspects will increase the final device cost that probably make it incompatible with consumables like IoT technologies. So your technology has to be compatible with the final application of where they have to be installed. Let's move now to one of the most important, if not the most important, parameter that investors or an industry looks when wants to enter in a market with a energy generator technology. It is the so-called levelized cost of energy. If you're gonna see the output of this levelized cost of energy, it's simply a number. But behind it, there is a huge work that will take in consideration all the little aspects, from raw materials to each manufacturing steps, all the costs, taxations, manpower costs, facility costs, and so on, in order to give you a common parameter from the energy generator technology, in order to compare with heterogenic power generator technologies. In fact, there are, let's say, several versions of this levelized cost of energy, but there are some that are more interesting with respect to the other, but you can use these algorithms only in the case you have a lot of data that you can use. In the case you are limited, probably you have to use simplified version that can still give you an idea, but it will not really good at the end in terms of if you want to use to evaluate your technology. So the levelized cost of energy is a way that allow you to compare power plants with different generating and cost structures. The one that is highlighted over here is the so-called complete annuity method. This is one of the most complete ones that, in fact, it is used by NREL and OpenEI for the comparison of different power plants. You can go to NREL website, dedicated area, and you can see a lot of materials on this. For the PV technologies, it is a little simplified, the formula, as obviously PV cells will not use fuel like petrol, so carbon, whatever, in order to generate energy. So, as seen over here, in the formula, there are a lot of factors, but the most important one is the capital cost. What is the capital cost? The capital cost is composed basically between of two parameters. One is the so-called total module cost, and the second one is the installation cost. Okay, the installation costs include all the parameters like installation labor, grid interconnection, wiring, all the aspects that imply the how much does it cost to interconnect, for example, your cells together and with the grid, and the cost of the module, that is how much does it cost to you to produce your module. Let's say, and it is composed by the manufacturing costs, and with the margin, okay, the overhead costs that you put on the cost, on the price that on the cost of your module. Obviously, for private companies, for industries, you want to make profit, so you have to consider how much profit you want to do on each pieces of device that you're gonna sell. And obviously, you have to take in consideration the power conversion efficiency and the incident power. The manufacturing cost is composed by the raw material cost, the engineering and production line labor, the utility cost, the equipment maintenance cost, and the depreciation of the equipment and the building. You have to take in consideration also that over time, your pieces of equipment get older, needs maintenance, or probably after some years you need to change them. And these are all costs that you have to take in consideration to understand if your technology is good and challenging with other power generator technology or not. When you start to understand and to want to calculate the LCOE, you have to understand, you have to take in consideration all the process from the beginning to the end. What it come out are numbers, are costs that give you an idea of how much that costs, material per material, layer by layer, your technology. So far, the most used, for example, to give you an idea on how materials can impact the cost of the final device, we analyzed the layout that include gold like back electrode. This is something that is not compatible with industrial production. Much lower cost, much cheaper materials has to be found and used, as the gold is not definitely a material that can be used for large production. In the analysis that we did, you can see that gold covers more than 50%, more than 60% of the cost of all the old materials that you use to realize your cells. Obviously, if you go larger and larger in production, the materials cost decrease, but some material, for not all the materials, like gold, but it is also true for silver, for example. They are commodities. The price is fixed by stocks exchange. So if you purchase 1 kilo or 10 kilos or 100 kilos, the price per gram is always the same. These things is not true if you move, if you analyze, for example, substrates or encapsulation materials or whatever. They reduce cost when you go larger in quantities. Even the material cost will mirror on the production cost. This is the cost that we estimated for the same configuration using the same materials, and also in this case, the cost to deposit gold is the one that highlight the most, and this will mirror on the final LCOE cost that for a small production is around 1.6 euros per watt peak, and for much larger production, it's around 1.4 per watt peak. This is another way to see the same numbers that probably makes more easy to understand the importance of some material respect of the other in terms of cost. Always goes encapsulation materials and substrate are the ones that are to be found. We have to address to the cost of such materials. Then we make some estimation. We said, okay, gold is not a compatible material for industry, so we have to move. What are the alternatives? Luckily, around the scientific community, there are some groups that are already exploring alternative back electrodes that are not metals or high-cost materials. For example, good candidates are carbon-based materials made by graphene, carbon black, or whatever. And just changing the back electrode with a carbon-based material and consequently changing also the deposition technique, the final LCOE will drop down to 0.7 for smaller production to 0.45 for larger production. That starts to make the perovskite technology challenging with the other more common PV technologies. Things that the LCOE of crystalline silicon panels on rigid substrate, let's say, it's around 0.3, 0.4 euro per watt peak. Things that gives a very good point for perovskite is that for flexible technologies, the LCOE, the one that are commercial so far, is around 1.5 euros per watt peak. It means that if we will be able to reach this kind of cost in terms of LCOE, the perovskite technology will be really, really, really challenging, if not the winner, against the other flexible technologies. Making these evaluations, we considered 10 years lifetime. So it is something that may be still achievable in the really short period for the perovskite technology. If we're gonna go a lifetime much longer, let's say 20 or 25 years, basically on rigid substrate, we expect to have an LCOE of the perovskite technology lower than the one of the crystalline silicon at this stage. Remember that when you go around, you will always find people that thinks to be better than you and probably will not consider you and try to not consider your job. But if you work hard and prove the goodness of your idea, also these people will change their mind and tell that you have to think outside the box. You have to collaborate with your colleagues always, because alone it's difficult to arrive anywhere. You have to always to collaborate with people. Question yourself always and stay united. Unity is strength. Thank you for your attention. I finished. So if there are some questions, I will be pretty happy to address them.
Thank you very much, Enrico, for your very nice talk and the valuable information that you give to the students. I cannot see any question now in the panel or even in the chat. Let's wait for a few minutes to see if someone has a question. Okay, I think there is no questions. If someone wants to write directly to Dr. Enrico, we are going to have all information in the presentations next week. So again, Enrico, thank you very much for your valuable talk. Here we have
Yeah.
a question.
Challenges.
Okay, Jacob Myers, say great presentation. I really like the discussion about the challenge. No, it's not a question. Thank you very much. Okay, perfect. So thank you, Rico.
Yeah, welcome, Anna. Bye to everyone.
Okay, so I think with Dr. Enrico's talk, we finish the morning session. As in the previous days, we are going to have a lunch break until 2:30 in the afternoon in Central Time. So we hope to have you all connected in order to finish the summer and to show a little bit about the Apolo project itself and the results that we have up to now. So thank you very much, and we see you in a few hours.
Good afternoon, everybody. Hope you can hear me. We are going to start in a few moments. Just to remember you that you will receive the quiz like yesterday at 3:30 on your email. I will also post the link here in the chat, and you have time to send us the results until 5 o'clock. So please remember that you will receive by email. If you don't receive at 3:30, it will be 3:31, 3:32, just depending of how fast is your internet. But don't worry that you will have the link for sure. Thank you, and we can start again. So please, Anna, your turn.
Okay, thank you very much, Joan. So let's start with our last session of this Apolo Summer School with tutors dedicated more to the European project results and the things that we are dealing in this very great adventure. So we're going to start with Dr. Bojan Boskovic. Thank you very much, Dr. Bojan, to be here and collaborate. I'm going just to do a very brief introduction. And thank you, Anna, for having here also representing TNT. So I'm going to just introduce you as the next speaker. So Dr. Bojan Boskovic is founder, CEO, and principal consultant at the Cambridge Nanomaterials Technology Consultancy Company, specialized in carbon nanomaterials. He has more than 20 years of hands-on experience working with carbon nanomaterials and composites for industry and academia at the UK and European level. He has a PhD from the University of Surrey, where his research in carbon nanomaterials has been used as a foundation patent for the startup engineer carbon science at Medit aircraft, the startup company Surrey Nanosystems. Previously, he worked as R&D manager at the NanoSeal, principal engineer carbon science at Medit Aircraft Banking System, research associate at the University of Cambridge, and as a senior specialist at the Morgan Crucible PLC. He was a board member of the British Composite Society and member of the steering and review group of the MINE EGT in nanotechnology, and an advisor to the UK government on the first nanotechnology strategy policy document. He has also worked as an advisor to the EZ on engineering and scaling, clustering and setting up of the European Pilot Production Network and European Characterization Cluster. He also has experience in exploitation and dissemination management of a big number of European projects, and also in the UK government-funded Innovative UK projects. He is also leader of two private consortiums, one in nanocarbon enhanced materials and the other one in advanced materials for additive manufacturing. So the session that Dr. Bojan will cover today we'll be focusing on intellectual property rights, including introduction of patents, patenting procedure and strategies. Thematics such as business benchmarking against competitors, trade-off between value creation and value capture, including identification, protection, exploitation of existing internal resources in order to gain a competitive edge, influence innovation through various techniques and frameworks to improve organizational performance and innovation in practice, which also be covered. So it's not a common talk in this kind of schools when we take a lot issues in a scientific way, but I think important to have this kind of information when we are a student to understand the complexity of the research European projects or research project in general, in order to have all the things clear and be able to perform the activities in the best way possible. So Dr. Bojan, thank you very much for being here, and the floor is yours.
Thank you, Anna. Thank you for your kind introduction. Today,
The plan was to deliver this presentation with my colleague, Dr. Jelena Aleksic. Unfortunately, she could not be here, but I'm joined with my other colleague, Dr. Anna Bankovic-Cassidy, who you see also in the screen. So we are innovation consultants, we are innovation management specialists, and the aim of the talk today would be to give you overview how to actually spot, protect, and take further intellectual property. So I'll share my screen. Okay. Can you all see my screen? Yes. Okay. Great. So I'll briefly introduce a company. So we have a sister company called CNT Innovation, which is in Brussels, and aim was to be closer to our European customers and develop the business further in the innovation management. This is briefly what we are doing. We help companies, universities, and government institutions to develop nanomaterial-related technology, products, R&D strategy, partnership, IP, and market strategies. We are specialized in carbon nanomaterials, so this is one of our strengths, and innovation management of various government-funded projects. We participated in European FP7 projects, and we have currently 10 European Horizon 2020 projects, and also UK government Innovate UK project. We could create a custom design project teams from the network of consultants from industry and academia, and help building supply chain. This is the brief overview of the projects where we are active. So those projects which are in the box are the currently active. They are ranging from biomedical application projects, such as, for example, Project NTRAC and MEDLOC. MEDLOC is about 3D printed graphene for biomedical devices, including the COVID-19 testing devices. Then we have projects related to environmental sustainability, such as, for example, Genesis or a Repair 3D project. Repair 3D, for example, is about recycling plastic and reusing that for 3D printed goods, such as, for example, ski boots. Apolo project, I don't need to talk about. You will learn in details in the following presentations from Anna. We have a project such as Graphosite, which is Innovate UK project about structural health monitoring on wind turbine, and many other projects. As Anna mentioned, I'm also leader of 2 private consortia that we running. So together with the Center for Business Innovation, one is on nanocarbon enhanced materials. And this particular consortium has been running for more than 6 years. We're just concluding the year 7. And AMAM, which is the Advanced Materials for Additive Manufacturing, which concluded the first year. And this has nothing to do with the government funding. These projects are membership-based, and we have among the members leading multinational companies. So, brief overview of today's talk. So I will first give an introduction about innovation and innovation strategy. Then I'll focus on the particular aspect of intellectual property, which is a patent. I'll also introduce a trademark and talk about copyright. So all of that are the aspects of the intellectual property. We will then focus on the protection of IP and on commercialization. So first, innovation. So innovation is about creating new value people are willing to use and pay for. So you might have a brilliant idea, but if there is no value which someone is ready to pay for, then strictly speaking is not really an innovation. To have successful innovation strategy is important to carefully plan and develop innovation management. So innovation strategy is the plan how to develop your innovation, and innovation management is actually delivery tool. So we are innovation management company. So this is our specialty related to various nanomaterials and nanotechnologies. And we help the people who working with us on the projects or our clients to develop the innovation strategy and to achieve the innovation goals they set up in that strategy. This is example of the elements in the classic innovation strategy, where you need to understand where you will play, what is your field, what is the game that you're going to play, what kind of products, what kind of markets you're going for, which part of the world you will sell that. And how you will win in that game. So what is your unique selling point? What is your value proposition? What is the difference between what you're doing and others that are already on the market? So how you will win? What capabilities must be in place? So when you understand how you will win, I'll have a different products, or I'll do different service, or I'll do it better, then you need to understand what kind of resources you need for that. So what kind of resources you already have, and what kind of resources you're missing in order to achieve what you have set as a goal to have successful innovation strategy. And then at the end, what kind of management systems you require. So when you get everything in place and infrastructure and so on, this is not one of a bright spark moment. It's a continuous process which will take a lot of time, and it would not be successful if you don't have successful management system to support that project. This is very brief explanation of the classic innovation process. So you have to determine objectives and strategy approach. You need to know your market, customers and competitors. So you will probably need to do some market research and understanding what and how you're targeting. You have to define your value proposition, and in projects that we're working on and with the private clients that we're working on, we are very often involved in this early stage of understanding what is the value proposition. And for example, on Apollo projects, we had exercises including identification of key exploitable results, identification of the business model canvases and value proposition canvases to understand how this value could be extracted from the processes, from the products that are being developed, and what is new, what are the customers, what are the channels to market, and so on. Then access to develop your core capabilities. So obviously market introduction, establishing your innovation techniques and systems. So running the system successfully over a significant time. As I mentioned, obviously innovation management and innovation strategy is very, very broad topic. We could have focused on many aspects, but today we're going to focus on protection and exploitation of the results. And I'll talk about various aspects of intellectual property and aspects of protection of that. And first and most famous and most well-known part of intellectual property is the patent. So patent is a form of intellectual property that gives its owner a legal rights to exclude others from making, using, selling, and importing an invention for a limited period of years. Usually that's 20 years, in exchange for publishing and enabling public disclosure of the invention. So the second part of this sentence is often forgotten. The patent is actually a publication. So bear in mind, yes, you do have protection, legal protection for 20 years, but you disclosing your idea, everyone would know about it. Everyone can read about it. And after 20 years, it's in public domain. So anyone can use it completely legally. So have that in mind. In the patent is usually refers to the right granted to anyone who invents something. And I would like to point out in those three words, which are in bold: new, useful, and non-obvious. So I'll talk in details, but the patenting procedure would need to satisfy all these three elements. So you need to prove, in order to have patent granted, that what you're doing is new, that it's useful, and that it's not obvious. As an illustration of this picture, I have just put a Lego figurine. I'm sure that all of you have played with Lego and you are familiar with a little Lego figurine. But I would like to draw your attention on the small print, as they say. So it says patented in December 18, 1979. So I would like to remind you that the patent gives you the right for a certain time. And I said, usually that time is 20 years. So this patent expire on the 18th of December, 1999. So in the last century. Bear that in mind. It would be important for next discussions. So let me introduce other aspects of the intellectual property. Trademark. Trademark is a type of intellectual property consisting of recognizable sign, design, or expression which identifies products and services of particular source from the others. The trademark owners can be individuals, business organizations, or legal or any legal entity. A trademark might be located on a package, label, voucher, or on the product itself. For the sake of the corporate identity, trademarks are often displayed on company buildings. It is legally recognized as a type of intellectual property. A trademark often has the TM symbol. There is other two symbols which are in context, and you probably seen also little R symbol that has been used like a registered, and SM is very rarely seen, but it stands for the service mark. Right, so this is example of what I have been saying. So maybe so far you didn't really pay attention on these things, but this is example of the Lego product and the copy of that Lego product which has been done in China. So I would like to discuss that in more details. First of all, as you can see, there is arrow showing the little TM sign behind the Star Wars sign. So you can notice that the copy, even though they are exactly the same figurines, and I would like to bring your attention to the comments that I just made a couple of minutes ago, that actually Lego figurines patents have actually been expired. So little people around this big monster, they are free to copy. So no valuation about that. So obviously there was no issue of the Chinese copy to have exactly the same figurines because the patent has expired. But what they were afraid of, the people who were copying, what they didn't copy here, they didn't copy Star Wars trademark, so they put Star Plan, and they didn't copy Lego because it's a trademark of the Lego company. So they put Lepin and words in Chinese. So basically, this is exactly good example of the use and abuse and copying of the trademark and the patenting situation. So the Lego Group purchased a license from the Lucasfilm in order to be allowed to launch Lego Star Wars. So Lucasfilm is the legal owner of the Star Wars trademark. And in order to use that, Lego Group has purchased a license. And if the copy had put the Star Wars, then obviously they would risk of either Lego or a Lucasfilm suing them, and they will have very clear example of the product that is available for sale, and it's obviously using the trademark without actually purchasing the license. So the last example for today of the intellectual property is copyright. So I'm sure again you have seen the little C. So copyright is the legal term that is used to describe the rights that creators have over their literary and artistic work. Very often copyright is used for books, music, painting, sculpture, films, computer programs, databases, and technical drawings. So essentially, if you are a software programmer, from the intellectual point of view, you are not much different to a writer of the book or a song or a musician. This is your intellectual property. Every line, in the code of your program is like a verse of the poem or a line in the book. It is treated legally completely the same. And if someone copies your program, 100%, they are in violation of your copyright. However, if they are clever enough to modify your program, then we are in completely different game. So I wouldn't go into too much details of the copyright. That's a very interesting issue that we could discuss in more details. My aim is, because this is a technology workshop, and most likely that working on the development of new technology, you would be in position that some of your work or work of your colleagues in the team is being considered for patenting, and maybe receives the patent. And I would like to focus the rest of the presentation to that. So this is example of a patent on the European Patent Office database. So you can see various elements in the structure of this patent. First, there is a title, in this case, carbon-carbon composite. Then there is inventor. I picked up one of my patents. And then you can notice various funny numbers and letters under classification, more of a similar type of numbers and letters on the application number and under priority number, and also published as. So let me explain you a little bit about that. So, for example, priority number, you can see starts with a GB, which is for Great Britain, and starts with 2007. So priority is 2007, means that this patent, and usually patents are filed first in the local, in the kind of national patenting system where the invention has occurred. So obviously this particular invention has occurred when I was in UK, and it was filed in Great Britain. But the priority number, which is 2007, and there is a date behind that as well, is something which is then transferred to anywhere else. So you can see that a US application, so a line above, starts US 2008. So in the following year, we had US application and we had a world application, so WO 2008. But they are all based on the priority number coming from the first local application. So simply speaking, you go, you file the patent, and that day is the day for all other patent applications. Then obviously you can see the abstract. This particular is the US applications, and you can illustrate the drawings. So this particular patent, if anyone is interested, was about carbon-carbon composites for aircraft brake applications. Obviously filed a long time ago when I was still working on this. Okay, so patentability assessment. So you have great idea, your supervisor, your colleagues thinking that it's a great idea, and you all thinking, maybe we should patent this. Okay, so what are the next steps? So patentability assessment is the first step. A patent search is the first step in the patentability assessment. So detailed analysis of the references of that search and the written report is usually what is the first step. So the aim of the patent search is to see basically has that been done before. But to be precise, has that been done before means, has anyone filed a patent? It could be done before if there is no publications, if there is no patents, if there is no evidence, then technically speaking, it's new. But if there is evidence that has been done before, then you need to know about this. So that's the aim of the patentability assessment. And as I mentioned, the patentability assessment includes patent search, detailed analysis, and analysis of the prior art. Patent lawyers often call these documents due diligence. And we, Cambridge Nanomaterials Technology, we are expert in preparing customized patent search reports. And we do that on the Apolo projects and on our other projects. And we do this for our private clients. So going further this is kind of common dilemma, patent versus publication. So I would like to clarify, I guess many of you already know, but just I'll start from the bottom line to avoid any problems. You should file your patent application first and then publish research paper in the academic journal. And I'll be very precise about this. So basically you can go and file your patent application today. Tomorrow, you can send your paper for publication. So that's the usual. To be honest, there is a little bit of game that you can play. Technically speaking, as long as your paper is not published, so not in the public domain, then before the patent has been filed, it's fine. But technically speaking, again, if you send your publication to the journal for a review, you disclosing idea. So the journal editor can actually basically intervene in the patenting procedure and bring it down if they want. That doesn't happen often. but it is something to have in mind. So again, I'll read the last sentence twice. So to avoid any problems, you should file your patent application first, and then basically send the paper for a publication, or send an abstract to a conference and make any other disclosure of that invention. Right, Coca-Cola. So I'm sure that I don't need to explain what is Coca-Cola, and I'm sure that I don't need to explain to anyone what is Coca-Cola drink. So it's a unique drink, extremely popular, and very, very interesting story from the intellectual property angle. So this is the copy of the patent and protection of the bottle design. So iconic Coca-Cola bottle that you can still see, here it is, and this is dated 1937. The original recipe has been briefly patented and then completely withdrew, and Coca-Cola never ever since filed the patent for the recipe. Answer is very simple, because 20 years from the moment you file your patent, it's in the public domain. Anyone can use it. So if Coca-Cola filed the patent at any stage during their production, and they are in business for far more than 20 years, everyone now would be able to produce Coca-Cola exactly to the same recipe, to taste exactly the same. And all of you know, and you tasted various other drinks like a Pepsi or million other versions of Coca-Cola, and they don't taste the same. So unique taste is the secret recipe. So in this case, this is the explanation why Coca-Cola never actually filed the patent. So it's kept as a secret, and some things are best to be kept as a secret within an organization. And usually what is recipe, what is the process is kept as a secret, what is the product is kept, is filed as a patent. Now I would like to focus on, so fast forwarding, you've done your patentability assessment, you were successful, your patent is granted, and you're happy, and you and your boss and your team are thinking, what are we going to do with that? Are we going to license that patent and make the money from the royalty fees? Been there, done that. Very nice. I've been, for one of my first patents, sitting at home and receiving 15,000 every year for doing nothing. It's nice. However, alternative option is to have a startup, a company that would actually use that patent as a foundation to attract investment. So bear in mind, we're talking about intellectual property. So it's a property, it has a value. So you're building the company on that value. And I'll talk about value and different concept of the value of the company, especially startup company, on the next few slides. So,
dear Dr. Bojan, sorry to interrupt yourself. We are quite 5 minutes out of the time. So if you please.
Sorry, I'm finishing. I just have.
Thank you very much.
Yeah. So, so this is what I just mentioned about the value of the patents. So usually you divide the value of the company of the tangible and intangible assets. So tangible assets is everything that we know: the furniture, the machinery, the building, equipment, computers, everything. But intangible assets is the most important thing. So that's the patents, logo, copyright, trademarks, and so on. So essentially, the message, the key message, if you're starting a startup, about 80% of your value could be in intangible assets. So you have a small company, you don't have a big shiny buildings and equipment and so on. but your biggest value is your intellectual property and your patents and other categories of intangible values. This is just a brief example. I would really love if this was in person. This is the last training we've done, and this is the picture of my colleague, Dr. Jelena Aleksic, talking to the students. This was done in January 2020 in Vienna, and we received fantastic feedback. It is obviously quite frustrating for me that I cannot interact, that I cannot see your faces, that we cannot discuss these things and the examples brilliantly in person or during the coffee break. However, I've seen there are already some questions, and I would be more than happy to answer. This is briefly about myself and Dr. Jelena Aleksic, who could not join me today. This is us. Thank you very much. Okay.
Okay, thank you very much, Dr. Bayer, for the very interesting and different talk that you offered today. I don't know if we have any questions in the panel. I can see them now. So as we are already 5 minutes later, maybe we can do as in the previous talks, Dr. Bojan, that if someone has a question, is going to put it in the panel and you can write the answer directly in the chat box.
No problem. Thank you.
Okay.
So I should introduce the next speaker, which is Anna, our chairwoman of this school. Dr. Ana Milena Cruz from Leita Technological Center in Spain is the technical coordinator of the Apolo project. Ana Milena Cruz has a PhD in material science from the Universitat Autònoma de Barcelona, a master in materials engineering from the Universidade Federal de São Carlos in Brazil, and a degree in physics engineering from the University of Calcutta in Colombia. In her training period, her research career has focused mainly on the synthesis and characterization of materials in the area of ceramic, glass ceramic, polymer, and biomaterials, focusing specifically on their electrical properties. She is currently developing her professional career at Leita Technological Center as a senior researcher in the energy and photonics conversion group. Within the group, she manages the solar energy area and works in the coordination, execution, and exploration of research, development, and innovation projects financed by public or industrial contracts at the national and European level. She has specialized in different technologies, including photovoltaic, thermosolar, printed electronics, and thermoelectric. Her work is related to the production and integration of devices, as well as characterization of the materials involved and the evaluator of their final behavior. And she is, of course, the coordinator of the whole project. So, Anna, thank you very much. You have the floor.
Okay, thank you, Hugo, for the nice introduction. So, I'm going to close this summer school with the summary of the project, and the idea is not to talk much about the technology itself, but try to explain you the aim of the Apolo project. What was the aim to present this project and to start working on this flexible perovskite technology? What is the relation with all the talks, the talks that you listened in the previous days with the activities of Apolo and the objectives of the project? And of course, a very, very general overview that what we have now as a result of the project, and what is going to be the last part to finish this project next year. So I'm going to start with a very brief introduction of who we are in LATEC. So we are a nonprofit organization expert in offering solutions to the technological needs companies and entities with orientation towards generating competitive value and sustainable future. So we are divided in 5 main areas: health and biomedicine, circular economy, energy and engineering, applied chemistry materials, and advanced technology services. And we are located in different cities or places of Spain, where we work at the different areas. So regarding the Apollo project, the main department on charge of the coordination is the Department of Energy and Engineering, but also the Department of Circular Economy and the Department of Applied Chemistry Materials is working in activities within the project. So talking about the Energy and Engineering division, we work in very wide aspects. So we cover Internet of Things, robotics and automation, additive manufacturing, integration and technologies adoption, and also, of course, energy conversion and storage technologies. Within this part of energy conversion and storage, I manage, as Hugo said, the solar energy area. So we are coordinating this project, thinking in promote the photovoltaic technologies as a future for the renewable energy. But let's go to the matter. So these days, the concept of smart cities are a very common concept in all the technologies. So renewable energies and smart cities are perfect binomial to accomplish a lot of challenges that the humanity have right now. But why renewable energy is so important? It's because with this kind of energy, we can take care of the health, because we can have a less polluted and clean air. We can contribute to the reversal of climatic change that it exists, and it's a real problem now for the actual generation. These kind of energies allow to economic savings of public money in medium and long term, and also promote the ability of the cities and the habitability of cities and the best quality of life in the inhabitants. It's not only a health matter, it's to improve the quality of life of the people. So with the boom of smart cities and of course the renewable energies, the trust in solar energy increased a lot. For example, just in 2018 in Germany, the emission of 29 million tons of CO2 equivalent was avoided thanks to the consumption of photovoltaic energy of 47.5 terawatts of electricity produced with PV, only with PV. So, but now as cities, as citizens and the cities take a very important role in the economy and the technology of the world, the buildings are presented as potential and renewable energy managers. So the production of photovoltaic energy is not only thinking in utility plants when you have a very big solar camp in the desert to get this photovoltaic energy and to produce the energy. But also buildings are now thinking as managers of this renewable energy and have a huge potential for the solar energy in general. So there are different ways to use the solar energy that can be produced by a building. It's not just to have the panel and produce energy. You can lead energy to the grid. The excess of energy that you produce, you can put it on into the grid. You can use the energy to self-consumption, to self-supply of the building, to not need other kind of energy to cover the power output that you need to the normal operation of the building. And also you can save on supplies. For example, with the electrical vehicles, you can also be a source of energy for this kind of thing, the things that are not inside the building, but that you need to be closer in a city. So let's introduce two interesting concepts in photovoltaics applied to the buildings. Since you can have elements that are attached to the building but not accessible from the inside. You can have elements integrated into the buildings but that are accessible from inside or outside, and you have elements that can be placed in both categories. So taking into account this, you can have two different groups of photovoltaics applied to buildings that are called building adapted photovoltaics, in where the PV element is a complement of the building without compromising the functionality of the structure of the building. And you can have the building integrated photovoltaics where the PV element is part of the structural design of the building. So you cannot just put it, you need to make the right calculations and the right modifications in order to integrate it into the building. Besides to have this division of elements to be integrated in a building, we have now a segmentation of the use of the photovoltaic elements in the building. So we can have two categories, principal categories. We can have the photovoltaic that can be located on the rooftop, that cover mountain systems, when you just put the panels like in an utility plant on top of the roof. You can have full roof solutions that are reintegrated in the structure of the building. You have you can have isolated tiles, skylights or solar glazings. You can have prefabrication systems and low weight systems to put in the top part of the building. But you can also think that the building can have another surfaces to be to integrate these photovoltaic elements like the facades. You can also have multi-systems. You can also integrate the photovoltaic panels in facades that are designed to warm or cold the building. You can also have prefabricated systems, lightweight systems, and accessories that are located outside in order to contribute that this production of the energy in the building. But we need to think also that the integration in a building need to be thinking or need to be conceived, taking into account a lot of things. So first of all, we need to think in the model. For example, you need to think taking into account the color, the material, the transparency, the size, the shape, the weight in order to integrate it. But we also need to think in how we are going to integrate this kind of model. We can integrate it thinking in efficiency, thinking in have the the best energy that we can have, or the most energy that we can have. We can integrate thinking in the multifunctionality and the aesthetic of the building, not only thinking on how many energy we're going to get, but how it's going to be look like the building. And also we can integrate thinking just in the elements separately, just thinking in the accessory that we are going to put in the building, the window or the balcony or the facade or the rooftop. Now the technology is not anymore a thing that can be thinking just for the producers of the technology, for the industrial point of view. We need to think also that the citizen at the end, it's the principal actor for these buildings that produce energy and is the principal user of a smart city. So we also need to take into account the added value that this integration can give to the building. You need to take in account the relevance of the different actors, the role of the architects and the designers, the role of the integrators, the role of the PV manufacturers, and the role of the scientists on charge of the development and the optimizing of the technologies. And of course, the consciousness of the citizens, because at the end, if the citizen is not convinced to put something in her own house, is not be we cannot think in commercialize a technology. So all the actors are important when you are thinking in include a PV element in a building. We have a great architectural works worldwide where integration of photovoltaic panels is used for recreational or office buildings, like for example, this football stadium in Taiwan or this Sanjo Solar Arc in Tokyo. And we can see that the dominant technology in the integration of photovoltaic elements in buildings are dominated by the crystalline silicon technology. With products with more than 35 years of continuing operation and covering from large photovoltaic solar panels to buildings integrated as community energy communities in the city. Also, we can find the thin film technology as another commercial product for building integration, but of course, the queen technology is now and in the actual time the crystallized silicon. But let's about the cost of the integration of the technology. As in the case of the utility plans, we need to take not only in account the cost of the technology, the fabrication of the technology itself, but we need to take in account all the projects. We need to see the cost of the installation, the electrical connection, the planet inverters, casting systems. But in the case of the building integration, the cost of the module is the predominant factor. Clamping system can also play an important role depending on the technologies, but you can see here, for example, that in the case of rooftop, the modules are the highest cost of the implementation of the PV project. So what are the problems or tendencies that we have in the actual PV elements that we have available in a commercial way? So we have the crystalline silicon and the queen technology, as I mentioned, with a very high efficiency, but black is the dominant color for buildings. So thinking a future with a black city is not something that it's really accepted by the designers and the community in general. Also, in the case of crystalline silicon, the modules are very heavy, so they involve complex structure and high prices to be installed. Also, we have the limitation in designs, texture and shapes. With the glass, a predominant material that it's a material that it's not low cost, and it's not easy to implement. In the case of the thin film that have a small portion of the commercial elements in building integration, we have a lower efficiency compared to crystalline silicon. So we need big areas to be in the same range of power output compared with using crystalline silicon. We have lighter modules, but with higher production prices, and also black or dark brown is the dominant color also for buildings. So we are in more or less the same situation than in the case of crystalline silicon. If we can see this graph here comparing the efficiency in the last years of the different technologies, we can see that in very, very few years, perovskite solar technology has positioned it at high efficiency technology with the efficiencies at cell level in comparison with crystalline silicon. So we can have here a potential technology that maybe is not necessarily necessary to be the replacement of crystalline silicon, but maybe can go to other markets or to help in other markets in order to increase the energy production by solar elements. So if we see this table of comparison of the three technologies that I mentioned, crystalline, thin film, and perovskite, we can see that we can compare it in efficiency in the three technologies. In the case of crystalline silicon, we have also good stability, and it's a technology that is very mature, so we don't have problems with the scaling up of the devices. In the case of thin film, we also have efficiency not so high that in crystalline silicon, but that can be used in the integration in buildings. A less weight than in the case of silicon. Also, we have products, scale-up products, but the stability is not so good than in the case of the crystalline silicon. In contrast, we have that the perovskite is a technology that have very high numbers in efficiency, can be conceived as a flexible technology, lightweight, light cost, with a very versatile design, but we have the problem that the stability is not so high than in the case of the commercial technologies. We have a lot of challenges that you saw during the different talks in the previous days. And also, we need to work in the scale up of these wonderful cells to see if we can produce also high efficiency modules, thinking in lower costs production to be competitive, or leads to be commercialized, as in the case of crystalline silicon. So for this reason, the concept of Apolo arises with the design of a full printed, flexible, robust, efficient, organic allied perovskite solar cell. So Apolo is Horizon 2020 program that belongs to the low carbon program that is related to developing the next generation technologies of renewable electricity and heating and cooling, and started in April of 2018, and it's conceived to finish in the summer of next year. So what is the concept of Apolo? The idea in Apolo is try to manufacture flexible perovskite models that are reliable, fully printable, with high efficiency, stable from the relevant agent test, and with a low cost production, and mix it with an existing construction product of the company Flexbed located in Spain that have a lot of flexibility and easy installation, big scale format, sustainable system, customized design, many materials to combine. So what is this product? The product consists in a mesh with ceramics or glass or plastic or whatever material bricks that can be easily installed in the building, not only thinking in the facade, also can be applied in the roof, in the floors, or in any surface available in the building. So the idea is try to combine all the benefits to have this kind of installation that do not require a very special personnel to do it, and put it also the PV elements with a very lightweight in order to conserve the flexibility of the product and produce energy. So this mesh not only is going to protect the building from the shadows, heating and cooling, and provide for a nice aesthetic, but also we are going to have energy to supply the needs of the building, and of course the energy community. So the idea is that we started from the state of the art, and the idea is that we are going to go to a medium technological stage in order to think in a future in a production of a real beer integration product. So we are a consortium with about around 11 partners in 7 European countries, and despite that we are a European project in research and innovation, we have a very balanced consortium, because we are 30% of the consortium belongs to the scientific community working in the development of the new the innovations of the technology, but we have also small and medium enterprises and large enterprises that are helping us to design this new product, thinking in the commercialization and the low-cost production from the beginning. So we have three main objectives. The first one is to develop a high efficiency and sustainable flexible perovskite solar cells, working in the different layers that you learned that we can have in a perovskite, working in the land management strategies described by Dr. Manuel in his talk, and applying the modeling described by Dr. Uli in the Franz Hofer's talk in the first day, and also the anti-solid content that you saw during the morning in the Dr. Anna Maria's talk. The second objective is the development of a long-time flexible module, working also in improve the stability of the material that will to conform these layers. Also using a novel low-cost encapsulation that was described by the Dr. Stefan Cross in the first day, and innovative integral testing to guarantee that these high efficiency and stable devices can be also flexible, because the flexibility is very important in this kind of applications. And the third one is the development of sustainable and scalable printing processes, using innovative low temperature processes, like the what described by Dr. Francesca De Rossi during the morning. We also are trying to design and develop a complete recycling process for the perovskite, because as was mentioned for the Professor Francesca Brunetti in her talk, the sustainability of the technology is very important. Try to manage what we're going to happen with the technology when it's once it's commercialized. And also we are working in the integration of these modules in a first prototype in the FlexBit product for building integration applications. So this graph can resume our objectives. We want more efficiency, more stability, less cost, and a green process also. But how is to ensure the symptoms of Apolo? Because all these things are more related with the research part of the project, but we need to ensure that the technology is going to be accepted at the end. So we have an economical assessment for low-cost production with a target of cost of 35 cents per peak. We are working in the standardization and common regulation of the technology, because all the regulations are related with silicon technology, that is the commercial one. We have not standards for this technology yet. And also we are using the environmental assessment, like the life cycle assessment and the life cycle assessment, not only thinking in the final solution, but also using these tools in the design of the devices. And of course, as Dr. Gordon mentioned, we are working in the exploitation strategy of the technology once we finish this project. So here you have the timeline of the project. So we start, as I mentioned, in April of 2019. And we spent the first 8 months of the project in the baseline definition, the state of the different partners, because we have different labs working on this. And we did the first selection of materials and process and designs to work in flexible devices. So we work with more than 38 configurations in the project. That is a very, very huge work in order to have all these objectives in the same device, because we have in the literature high efficiency cell, we have more stables, we have maybe something with related with local production, but we don't have all in the same element. So it's a very big challenge to have only one. So in the second part of the project, we did the first selection for encapsulation materials that are compatible with the devices that we are trying to develop. We defined the strategies for the recycling for a future recycling processes, and we did the final selection of the materials and processes in order to have the final modules at the end of the project. In this period, we were mainly in flexible devices. Even we conserve the work done in rigid devices just to compare and to see if we can maintain the properties when we go to flexible substrates. Of course, as in the case of all the projects, I think in the worldwide, we had problems with the COVID situation that caused delays in the work. But we are now trying to solve this problem, and we continue working a lot in order to accomplish all the things that we promised at the beginning of the project. So here we have a very, very general summary of the result that we have now. So in terms of efficiency, we have rigid cells at 22% of efficiency. That is a very high value for the technology. But also we have flexible cells more than 19% in the case of cell level. So we are in a very, very good position for flexible devices. And we also are working at module level with 18% efficiency in modules of glass substrates and 12 in the case of flexible modules. With the light trapping structure that are being developed by Uninova within the consortium, we have a scheme with up to 19 enhancements in the photocurrent for a fifth batch of photonic extraction, and we expect in the last year to have at least more than that in improvement. So our efficiency targets are more or less guaranteed. And we have new advanced characterization methodologies for highly resolving imaging and chart extraction and recombination, because it's important to get the objectives, but also it's important to understand what is happening in these devices in order to improve them and optimize all the process. In terms of stability, we have a full set of agent tests defined for the project, taking into account, as I said, not only the standards from silicon, but also the standard that need to be accomplished for thinking in a building integrated product. From the test that we have in the case of glass devices, we have that we don't have more than 10% losses in very, very critical conditions, like 85 degrees and 85% of relative humidity in 800 hours. And we don't have losses after encapsulation. That is a very, very good result. And in the case of flexible, we cannot have the same stability that in the case of gas encapsulation because of the reason mentioned by the Dr. Stefan in the previous day. But we are also in a very good position with the less than 10% and losses at 400 hours. The complete test to reference is 1000. So we are more or less in the middle of the test. So we also have a new class of encapsulation materials totally developed that are being applied to the new devices. And we have a specific testing regarding mechanical properties for this kind of devices that it's a new thing in the photovoltaic world. Taking the best testing that we have in the printed electronics, and we are trying to apply it here in order to guarantee the flexibility of the device. In the case of the green processing, we have 6 potential green solvent candidates to replace the toxic solvent that we have in the perovskite mentioned by the Professor Brunetti in her talk, and 2 in phase of device testing with not so good results in efficiency, but we have functional devices that is also something new if we compare with the state of the art. Also, we have the LCA reference cells screening ready with results and recommendations that allow us to identify the goal as the main constraint, and was also mentioned by Dr. Enrico in the cost and application task that he did. In terms of recycling, we have the development of microwave-based recycling process to extract the lead from the perovskite at the end of the life of the device. The strategies are defined for glass and polymer. In the case of the polymeric devices, we found that these kind of technologies are not suitable to be applied, since we destroyed the substrate during the process, but we are working in an alternative solution for this kind of flexible. So we are going to have the complete pack. We are going to have solutions thinking in the technology and not only thinking in the project. Finally, we have the integration in a real BAPV product. We have the optimization of the performance losses in the modules due to the contributions of the interconnections and all the things that we need to deal when we construct a module. We have a proper design definition for the modules to be integrated in this kind of products. We have the first calculation of the cost of the technology with the present scenario that maybe is not the goal of the project, but we still have 1 year to work in that. But we know what are the main constraints to not have this target achieved. And we have the starting point to optimize all the technology in order to achieve a low-cost production. And so we have a very, very nice result in metal foil as second substrate in order to give to the construction company different solutions for this kind of construction meshes. And not only thinking that we have the polymeric one and we need to just to attach this kind of module to the product, but we can play with different surface colors and appearance of the building to give to the architects a solution that can be thinking in an aesthetical mode also. So we have the demo design definition according to the modules and marking orientation, of course, to show the potential and versatility of the Apolo perovskite molds. We have 3 different demonstrators. Unfortunately, I cannot show images of the products right now, just for the protection of the intellectual property of the project. But just I can say that we have different objectives with these demonstrators. The first one is to demonstrate the high efficiency models in polymeric substrates. The second one is to demonstrate that we can change this kind of polymeric substrate for metal ones with less efficiency, but with an alternative in terms of aesthetic and the properties of construction in the building, better properties to corrosion and different image of the building. And also we have a third demo where we are going to play with the passage of light. It's going to be with the same high efficiency structure, but we are going to separate a little bit the cells in order to allow to the light pass through the building element in order to have another visual of the building. So we are going to have 3 very interesting products. What next? What do we need to do to finish the project? So we are now in the scale-up phase. We have 9 months of manufacturing of the modules and stability testing of the devices, and also the assembly of the demonstrators with the optimized models. And finally, we are going to pass to a validation phase, 9 months also of testing of validation that all the innovations of Apolo are okay, and that we can guarantee that the objectives that we had at the beginning of the project are already achieved. So I think that that's all for my side. I know that it's a very, very general view of the project. It's difficult to summarize 4 years of work in just 30 minutes, but if you have any questions, please do not hesitate to do it.
Okay, thank you very much, Anna. As you can watch your email, you received the quiz. So I will also paste it here on the chat. So if someone of you needs the quiz link, you will have it here on the chat, as well as in the email. Thank you very much. I give you a word just to finish to Mr. Hugo and Anna, if you want to finish the sample school.
Well, I can start.
So I think it was a great summer school, in my opinion. All the talks that I assisted was very high level, and I think the students could appreciate that, and I hope so. And I hope they have learned and they have been very profitable for them. So this was the main objective. So thank you for all the students that attended this summer school. And also thanks to all the speakers, which were amazing, and the way they tried to explain all the concepts behind the solar cells and this and their technology. This was very high-level presentations. So I think everyone needs to be congratulated, and I'm very pleased the way this summer school went.
Manuel, do you want to say something?
Sure. Yes. So I joined my words with Hugo. So just want to thank everyone, the speakers and the attendees. So yeah, this was an excellent school. I was also very pleased with the high level of all the presentations, and also with the good with very high attendance that we had in along these 3 days. So yes, thank you everyone. And even though we didn't make the school presential, I just wanted to tell everyone that you are always free at any time to come and visit us in Caparica. I'm sure that maybe this could extend to even the other institutes of that participated here. So, well, when you want to visit us in our installations, it's just a matter of sending us an email and we can make you a tour. So yeah, you're welcome always. Thank you.
Okay, for me, I just to join to the comments from Hugo and Manuel, and thank to everyone the very excellent response that we had in this summer school. I hope to give you different things, not only regarding the technology itself, but also to show all the students how a European project works, and on all the things that involve to have a project. That I think is important also, not only for the people who is going to continue with the academic career, but also the people working in the industry. But because at the end, if we don't have the match between industry, between citizens, and between research, we are not going to have good solutions, and we are not going to be able to improve our quality life for a better future. So thank you very much to everybody. All the information, the talks, and the presentations are going to be shared with all the participants during the next week. So thank you very much. And Joanne, I don't know if you have information about certifications of the summer.
Yes, regarding all the information with presentations and videos, you will have it on the Apolo website. You will receive emails with information, so don't worry. And about the certifications, you will receive it by email directly to your email. So during the next week or the next 2 following weeks.
Okay, so I think we can close the summer and just have a very nice weekend. And I hope you maybe see you in other kind of events, or in other European project or research project in a future. So thank you very much to everybody.
Thank you very much also. Bye-bye.
Bye-bye.
Bye, have a nice
Bye,
summer.
thank you.